live. Let's check the audio. Okay, we're live. The audio seems okay. So this is, normally if I speak too loud, does it still ring? Let me listen to it. It still rings a tiny bit. Yeah, I don't know where this comes from. There's some USB device which does a lot of EMF and which blocks this. But it's okay, good enough. So this is an update of the IOVoodoo, and the last time we stopped 3 weeks ago, so a lot of time has been spent on it, and I've almost only worked on it. So we'll have a really quick summary of what the IOVoodoo is, because it's been 3 weeks and you probably forgot. Else you can also watch the previous stream. But the IOVoodoo, the purpose of the IOVoodoo is to combine these two devices, the SVG finder and the IO finder. It's meant to be a tool for reverse engineering. The SVG finder is there to find the SVD and JTAG ports on up to 16 pins. So the purpose is, the aim is, you connect any board to it which you want to reverse engineer, and you want to find if there's a JTAG port or an SVD port. Well, if you find test points or test pads or connection points, you just connect them here. You provide the target voltage, and the SVG finder will find JTAG or SVD on the port. I've designed this because the one I had didn't work. The JTAG relay I used sometimes works, sometimes it doesn't work. I wanted, and if something doesn't work, I create my own tool, and this is a tool I created. Since I created this, which works okay, has its limitation but works okay, I created this thing, the IO finder, and the purpose of the IO finder is not only is to detect what kind of signal this line is. If it's an input or an output, you still have to put the brains on it, but it helps you detecting if one of the channels is an input or an output. And this also works, and I wanted to combine both of them. That was the purpose of the IOVoodoo. And we can see from the description here what the IOVoodoo or the IO finder is. Combined SVG finder, exactly. That was the summary. 16 channels. I want to connect up to sync. Scan for JTAG and SVG. Scan for UART port. This is what the camera doesn't work. So I've been showing plenty of things without the camera working. Let me restart OBS, because then the camera should work. And now the camera should work. Let me test if the audio works. And it's still ringing a bit, but that's okay for now. Oh, it's ringing a lot. Okay. Let's not couple it to the other things. So, again, so these are the two devices. These are the two devices. The SVG finder, which has been described. This is the SVG finder, which is there to find JTAG or SVD. That's the first device. IO finder, which is there to test the IO signals, if it's an input and an output. Helps you. It doesn't do it by itself. It just helps you. And then it also scans for UART. I'll show a demo of it. But the purpose is to determine the baud rate of the UART, and if you find the TX of the board, you can check all the other channels to find the RX. These two devices are based on Mini F4, and so here we have level shifters. The level shifters are there to interface between 1.5 5 volts and 5.5 volts to this microcontroller. That works okay. This is just to control power output to the voltage target. And what I do is just I implemented JTAG and SVD protocol in the microcontroller, and this way I can listen to all the ports or change all the ports or use any of the GPIOs, because it's a software bit banging. I can use any of the GPIOs to speak the protocol. There's no hardware support with defined outputs. So this is what this is. This is why we can use 16 voltage translators. On the other side, on the I/O finder, I have one analog multiplexer, and this allows me to switch between the 16 channels and put it to the analog input, and by pulling up or down the signal and reading the voltage, I can find out if it's high, low, pulled up, pulled low, and this helps you guess if it's an input or an output. Now, why can't I combine both of them in one board? Because this analog here, these voltage translator, they put some load on the channel. They pull up the signals. So the multiplexer, so this the target voltage will be pulled up. So using the analog multiplexer just puts some random value or some non-accurate value, because of the voltage translator you are already pulling up the signals, which is not good. There are other voltage translators, but we'll come to that. That's one of the reasons. The other reason is that I do software big banging for SVD and JTAG, but this is pretty slow, like something like 500 kilohertz. It is fine for detecting. If you want to use it for communication, it's not good enough. It is far too slow for communication. So what I want to do is use hardware peripherals to detect, to speak the communication. For example, UART. This board, I use the hardware UART. So I use the analog multiplexer to switch to the RX and TX pin, and this way I can use the hardware UART. I can speak very fast. 1 megabit per second is not an issue. 2 megabit should also work. I haven't tested it though, but it's rare to find serial which is over 1 megabit. And for JTAG, you want 1 megabit or more to transfer data for flashing and so on, because the initial purpose was just to find the JTAG and SVD, but the later purpose is to use this board as an interface, because once you've got all the cables connected and you know which pin is what, why not use the same board to act as a JTAG adapter? And you already switch the right lines instead of disconnecting the pins, reconnecting the pins on your JTAG adapter. Same thing for UART. If you found the UART pins, why not use this board also to speak UART, because you already can do it. And you don't want to plug and unplug the cables all the time, because every time you plug and unplug a cable, something can go wrong. So just use this adapter board as an SVD and JTAG adapter. Same thing, I wanted to do an SPI scanner for scanning SPI memory, something like flash chips, where the firmware would be. Since you want to reverse engineer, you also pretty much want to dump the flash content, if there is flash content. So I want to use the SPI peripherals. The issue with this microcontroller and almost all microcontroller is that the hardware peripherals is restricted to a couple of pins. So I cannot put the output of the SPI peripheral to any of the 16 channels, same for the input and so on. So this is kind of a huge restriction. A way to circumvent this restriction is again have the analog multiplexer, and for each channel you want to input output, you multiplex the signal from the analog multiplexer into, or could be a digital multiplexer, into the corresponding SPI pin or UART pin and so on. But this would mean that we need at least 5 additional analog multiplexers, because for SPI you have clock, MOSI, MISO, we have chip select. So these are already 4. For JTAG, JTAG needs 4 signals at least: TDI, TDO, TMS, TCK, and then we also have UART. So it's plenty. So you need at least 5 of them. 1 for the analog, 4 for the digital, if you are clever enough and can combine the different protocols to common pins. But if you want, for example, JTAG and SVD, as JTAG and UART at the same time, you need 6 analog multiplexers, which is quite a lot. So I wanted to design a new board which does everything with that, and this is actually what you see here. This is the STM because I already had code working with it, the IO finder and the SVG finder. So we needed 1 multiplexer for the analog part, and then at least 4 multiplexers for the rest. Because I didn't have enough pins to control all the analog multiplexers, we also need shift register. So with the few pins that this board has, we can control the 5 analog multiplexers, or the 5 multiplexer. And what I also want is level shifter. I want it to be compatible with 1.8 volt to 5.5 volt, because this covers pretty much all the electronics you would like to reverse engineer. The problem is that the multiplexer, you cannot use any of the lots of multiplexers are not really compatible. You don't know which of the channels is an input or an output. So you need some kind of multiplexer which allows input or output. There are multiplexers which do level sensing, which do automatic detection. The problem with the automatic detection is that most of the time it doesn't produce really, really sharp edges, which is a requirement for JTAG and SVD. JTAG and SVD don't rely on an internal clock. They only rely on the edges provided by the JTAG adapter. So you want really sharp edges, else you will have crappy signals. And I think this is why the device I use doesn't work. Sometimes it works, other times it's because they use auto-sensing level shifter. Like this is almost an auto-sensing level shifter. I didn't test all the auto-sensing level shifter, but I know there are level shifters which you just define if it's an input or an output, like this series. Which one is it? Create path library. Level shifter here. These ones. There you can define in ports of 8, but there are also these ones where every bit you can define if it's an input or an output. But it means that you need, again, 16 channels to control it. You can use it. You can do that with these shift registers. So we have analog multiplexers, level shifters, and shift registers, which was quite a lot of devices. And I looked around and I found another solution which actually combines another microcontroller, which I didn't know previously, which combines all of these things together. And this is what I've been doing the last 3 weeks. I've created a demo to know if it works. Well, this is the breadboard, so this is the demo. Now, let me disconnect the probes from the logic analyzer, because we don't need the logic analyzer anymore, so you can see what it does. This is the board. This is a Cypress PSOC 5 demo board, dev board, which is actually really nice. I like the schematic, I like the board, and it uses one of these PSOC microcontrollers. I don't know if we can really call it a microcontroller because it does a tiny bit more than just microcontroller. You can do digital, and so PSOC is programmable system on a chip, and the system on a chip means it's just a tiny bit more than a microcontroller. You have the microcontroller part, which is flash, RAM, and the CPU, which it has some kind of peripherals. It has an ADC, it has a DAC, but what's most interesting, it has an analog. You can do analog routing and you can do digital routing, like you would do. The digital routing is like you would do on an FPGA. The analog routing is like you would do with analog multiplexers or with some PLDs. And this is integrated into this chip. So this allows us to mix any of the pins, almost any of the pins, to any logic or any peripheral we want. It has also the really huge advantage is that the IOs are 1.5 or 1.7 to 5.5 volt compatible. You can have several power domains. So one of the ports could be at 5.5 volt, the other port could be at 3.3 volts. And I didn't find any other microcontroller which is capable to do that, all of them. And this also removes the need. So having the analog routing removes the need of having an analog multiplexer. Having the digital routing, it removes the need of having multiplexers to map the hardware peripherals like SPI to the pins. And then having the power domains or the huge voltage range removes the need of having voltage switcher. Now, all the work I did, it took 3 weeks, so it's a lot of effort just for doing like this. I think in the 3 weeks I could do the same with these parts and lots of other components. But it was the opportunity to actually work with this PSOC modules. So, and I implemented all of this in this PSOC module, and I don't need any other external port. These are all the connections. So this is the analog domain. This is where I measure the voltages. This is the digital domain. And here we have a USB to UART converter, which actually also provides 3.3 volts. So this is the target voltage. And here we have, can I show you? Here. This is the USB to UART converter. And this will act as a UART device. Here we have a microcontroller which has a connection with JTAG and SVD. And here we have a couple of, doesn't matter. Here we have a couple of connections to actually test if it's an input or an output. Now let's test if it works. So let me switch to this, clean the output. Let me switch to the screen. Full screen. I need to increase the font so you can see something. So this is the code which is now implemented in this microcontroller here. We have plenty of things which it can do, and for example, we can try to define the type to find out the type of the pins. This was the purpose of the IO finder. If I type, it scans through the channel, and it found that lots of pins are floating, which you can see because they are not connected. This pin is high. It is connected to the here we have the target voltage around 3.3 volts, and this finds out that this is really connected to the high load. Even if it pulls it down, the voltage is very high, and this tells us that this is an output. Either it is connected to VCC of the target board, or it is an output of the target board. And actually, it is the TX line of the USB to UART adapter. Then we have another signal which is pulled up. Something which is pulled up indicates us that this is either an input for the target board or something which is open drain, input or output. And in fact, it is connected to the RX line of the USB to UART converter. And here we have other devices. Most of them are floating because they're completely disconnected, so we don't know what they are. But here we have pulled up signals. And I think this is SVD clock and SVD data. I don't know exactly. And here are the test connections. So this is connected to the ground. This is actually really pulled up by a resistor, which is right. Yeah, you cannot see it. Here we have a tiny resistor which pulls up the signal to high. And then we have another cable which is connected to low. And this really helps you telling you what kind of device something is. So this is the IO status, the IO finder. What you can also do with this is monitor the channels. for activity. For example, if I monitor now, we have the signals of all the channels. And if let's check USB, not this one, here USB 0. Now this is connected to the USB to UART converter. If I type, you see that we have signals on line 0 and 1. And actually the signal is on line 1. This is just crosstalk because we see that it is floating, and everything which is floating is really susceptible to crosstalks when the cables are next to each other. I think in monitor you can actually pull up, let me check, H like help, yeah, monitor, I can, if I press monitor 1, I pull up the signals. This is what you see here. The signals are pulled up. And now if I type again, we see only channel 1 has some activity. And you could see the activity of any of the pins. And this helps you to identify when a board boots if there is an activity on one of the pins, and identify which is a data pin or which is a clock pin. Once you have identified the activity, what you can also do is actually find out the frequency. For example, if it's a clock, something like this, we know there is kind of data. If it's something which is variable, you can find the clock. So for example, we will test the frequency of channel 1. Now it monitors channel 1, and if I press, it tries to figure out the frequency of the channel. And if we can see here, we have a frequency of 57 kilohertz, and this corresponds to a baud rate of 1115, which is the double of the device. Sometimes it is low simply because bits are not always one cycle up, one cycle down. But it helps you identifying the frequency of the clock or of the data rate. Once this is done, we have, what can I do? UART TRX. Now we have, it detects the configuration, the serial configuration of the channel. Let's put channel 1. And now if I stop pressing some data, we can see that it found the configuration of this channel port. It is this frequency, it is this configuration. So this frequency, baud rate, 115 kilobits per second, 8 bits, no data bits, no parity bit, 1 stop bit. And if I continue typing, if I continue, no, wrong keyboard, wrong window. And if I continue typing, you can see in live what I type, garbage. So it can find UXTX. It can find the RX port of, well, the TX port of the target board. Now let's disconnect the serial and data project IOVoodoo. Is it an IOVoodoo? IOVoodoo. Is it here? Serial echo. Yeah. If I enable the serial echo. So serial echo. So now we want to find the RX pin of the target board. We know the TX pin is on pin 1. We know the configuration of the UART, and very often on target boards you have a login prompt which echoes back everything you type. So if you type a character, it will send the character it receives back, so you can see that there is activity. And if there is an echo back, we can actually figure out which is the RX pin of the target board. And this is why I have here the serial echo. It echoes back everything it receives over the serial port. This is the UART TX. We have to specify the TX channel, which is channel 1, the baud rate 115200, and yeah, the configuration 8, no parity, 1 data bit, exactly what we found here. And if we start scanning from the channels, we see that there is kind of activity. It sends some bytes, and if the bytes are echoed back, it says, no, I found the RX pin. So now we know that the TX pin of the board is pin 1, the RX pin of the board is pin 2. This works also nice. We also have the JTAG scanner. And we have the microcontroller which is connected here. It's connected over JTAG and SVD. And if we type JTAG, it will try to find out, wow, there's plenty of noise. This is because we finish. This is because we have the UART which was echoing back some data. So let's try to finish the scan. It doesn't, it takes something like around 10 seconds to go through our scan. We could make it faster, but just limit the number of channels. Yeah, I'll show you afterwards how we can limit the number of channels. It should be faster. Last time I tried it, it was faster. And I cannot interrupt it. No, I should add something to interrupt it. Again, this is demo code to find if this device works for the task counter. Yeah, let's reset it. So JTAG. Let's scan it for the JTAG candidates, and here you see that's weird. The scanning. I know why it took so long, because it does scanning in two parts, and the second part takes really long. It takes a lot longer. So first it tries to find out these channels, and here it found one JTAG device on these lines: TCK on pin 9, TMS on pin 10, TDO on pin 12. We don't know what TDI is, but on this device it found two taps. So at JTAG, I think target access points, something like that. Because you can chain taps, JTAG taps on, you can chain them on the same lines, and most microcontrollers already have two of them. The ARM part, we see that there is an ARM part, and then we also see the part here, which is an STM32F100 device. So we found these pins, and once it finds these pins, it tries to scan, is there a TDI pin? And this is what you find here. It scans for TDI, and it found TDI on channel 11. So now we completely found the JTAG port, and it works with the board. This board wasn't detected by the JTAGulator I had, and this was the start of the project. And here we really find the JTAG port. We can find other JTAG port or configurations. I need to add the break options though, to break scanning as we've seen before, or just press reset. Now we can also do the same for SVD. We can scan for SVD, and it finds plenty of garbage data, but here garbage data, this is because it is floating. So actually I should remove, I have to add some check that if it's 0, then it is nothing, so it doesn't put any SVD. But here it found an SVD port, and again we find the ARM port, and this is actually the SVD. It decodes also the ID code of the SVD device, and this is really the SVD of this microcontroller. So SVD works, that's fine. And we also have channel. Yeah, this is useful. You can actually reconfigure the channels as general purpose I/O, and the advantage is that when you know what something like is a reset pin, or you know that it is high because it is write protect, you can also connect this and you can control it. For example, we can say channel 0 is, we use push-pull configuration, and we push it high. P high, just pull high. And now we have channel 0 as output, push-pull, driving mode, and it is pushed high, which we see the channel is now here. Now, if we have this, we know that we will not scan for an input on this channel, and we also not scan on an output on this channel when we do the UART tag. And for example, if you have pins which you don't care about, let's say the last 5 pins, so channel from 10 to 15, we don't have, they are not connected. So NC, not connected. Now this configuration is not connected, and when we scan for SVD or UART, it will only scan on these pins, which will make it a lot faster. And the purpose is also to have its input, we know that if it's an input or an output because we know if it's a clock. And if it's an output, it can help us driving some signals like white protect signal, reset signal, and things like that. That also works. So that was the demo for the last 3 weeks. And yes, the advantage of not using voltage translator or voltage shifter is that we can now use, so voltage shifter are either push-pull mode or open drain mode. They don't provide both features. They can be kind of operated both ways, but yeah, these are the two main configurations. And because I am driving all the GPIOs, and all the GPIOs can have 1.8 volts to 5.5 volts, I can really configure them as open drain or push-pull. And I don't know of any other microcontroller which is able to handle all this complete voltage range on any of the pins. Or no, I don't know of any of them. Maybe one TI, no, I don't know of any of them. And because, so this is the code. What I really don't like, the huge, but really a huge letdown for this PSOC device is that you have to use a Windows device. So I had to install a Windows on a virtual machine here and use their proprietary device, proprietary thing. That's a huge letdown. So the advantage of the PSOC is that you can route all the signals, and yeah, you can route all the signals. So here we have the 16 channels, and what I did is this here in the inputs, I can select which of the 16 channels using a multiplexer goes to the UART RX line. This is here. Here we have the UART peripheral. This is a signal code going in. And because of that, I can now select which of the pins goes to this peripheral. So I can map any of the 16 channels to a UART peripheral and decode really fast speed, 1 megahertz or 1 megabit per second is not an issue. Same thing, I can put any of the 16 channel to an SPI adapter, to an SPI peripheral. And the idea I wanted is to scan SPI memory and be able to flash SPI memory in this device. And now I can. What I also wanted to do, what we see, so let's finish this. What I wanted to test, we see it in the features. Yeah. High-speed SVD using SPI. I've also tried that. It kind of works, but it's not ideal. Let me explain why. For that, we will have to look at the SVD protocol. This is also why so this high-speed SVD over SPI, this is why I have also this SPI thing. I wanted to reuse them to speak SVD. Sure, the main purpose is memory, but I wanted to try if SVD works. So let's have a look at the protocol, SVD protocol. So this is a really good diagram which explains how it works. We have a clock line and we have a data input-output line. It is half multiplex. Sometimes the master speaks, sometimes the slave speaks. At the beginning, the master speaks and sends a command. Here we see master is the host, the debug adapter. So it sends a command which tells the device, this is the command you need to do this. The target, so the target board, in this case the microcontroller, will acknowledge this, and then you will send some data or receive some data. And there are two cases. You don't see the thing on the left. Yeah, this is better. There are two cases. Either it reads or writes data. For example, so what we could do is because we're switching between, because it is half duplex, sometimes the host is sending, sometimes the target is sending. And it is not like in I2C where it is pulled up, but really one of both parties is driving the line. This allows you to have really high speed. You know, as I2C, It's generally used 100 kilohertz clock, 200, 400 kilohertz clock, very, very rarely megahertz. But for SVD, you want to speak 10 megahertz or even faster. And the only solution is not using pull-up resistor and operating the line in open drain mode, but having the host or the target drive the line. So every time you want to switch, we have a turnaround cycle, which allows to switch from on the host side from transmitting to receiving, and the opposites or the reverse on the target. Now, can we use SPI? Yes and no. SPI, you also have a clock. This is SCK, the SPI clock. Here we have kind of 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. And then we have the turnover. So what we could do is over SPI send 1 byte and then switch to reading data. And then we would have this byte, we don't care, and then we read the whole rest using SPI input. This works perfectly fine. For reading, which is here, yeah, exactly. We have the acknowledge and then we have the data. For reading, we can use a SPI peripheral. We switch just after sending the command, we switch back. The problem is that if we want to write some data, which is actually it was previously. So this is if we want to read some data from the target. And come on, where is it? SVD operation. Here. If we want to write data, this is vData. Actually, the target sends an acknowledge, and then immediately afterwards we send data. The issue is that with SPI, your peripherals, you are bound. I think the minimal word is 8 bits, 1 byte. Here we have 1, 2, 3, 4, 5 bits of acknowledgement where we read data. And then we have to switch back to transmitting. The issue is that the SPI peripheral doesn't allow you to change the lines between receiving and transmitting at the same time. You can cheat and having the first 3 remaining bytes in open drain mode and read data this way. If you connect together MOSI and MISO and you operate it using open drain mode, the device will actually so here in open drain mode, while the device is sending, you are not pulling the lines, so you are sending 1, 1, 1. This allows the target to actually send the data by pulling the data line low. That works fine. The issue is then after the 5 bits, the open drain mode is driving, well, the open drain mode can be used to send data. So the first 3 bits are sent to the target. This works, but the issue is that in the first 3 bits, you are in open drain mode. And in open drain mode, you cannot have really fast clocks, really fast speed. So in these first 3 bits, you would only be limited to 100 kilohertz or 400 kilohertz. But the purpose of using SPI would be to go above 1 megahertz. So it removes, you can do it using SPI by cheating and using kind of open drain mode for a couple in the right operation for a bit of time, but it removes the whole purpose. So at least you don't have to write the protocol yourself because you can use the SPI peripherals, but it removes the advantage of having really high speed communication. This is why you cannot use, well, if you want to operate SVD the correct way, where you drive the pins and at really high speeds, you cannot use SPI for speaking SVD simply because you cannot change the mode within 1 byte. So optional features, high speed, using SPI, that does not work. Let's talk about JTAG. You also want to have high speed of a JTAG. JTAG, you have these lines, TDO, which is data out, TDI, data in, TMS, and clock. So you have 1 clock and 1 TMS. It means you are already using 1 SPI device just to send a TMS signal. You need a second SPI device to actually read data, send data out, and read data in. So for JTAG, you need 2 SPI devices. what you can do is have your SPI, second SPI device being the slave of the first one, and this way they share the clock line. That works. The issue with, so that works perfectly fine. From an electrical point of view, you can use that. The problem is the layer above. In SPI, you are sending bits to switch data. For example, if the TMS here is low while the clock is running, you go to this state. And as you can see, the states are already bitwise. So the issue is that whenever you are sending data over SPI, you have to send 8 bits. So you really have to pre-calculate the 8 bits in advance if you want to do something really precise, because the 8 first bits where you set the right path needs to be configured, needs to be pre-calculated. This works really fine if you know the exact transaction from beginning to end. But if you have an SVD adapter or JTAG adapter which goes to the shift register for a couple of times and then wants to go to this shift register, then it will do a couple of operations, a couple of bit flips, but not 8-bit flips to go up to here. It could do 5-bit flips, it could do 16-bit flips, and now you really have to respect the number of bits to go to the right state, because and that's the issue. You don't have this 8-bit boundaries. If you do from the start, you can keep staying in the test logic reset and go to the right state at the right point in time, and then read the data. So using JTAG, using SPI for JTAG works only if you know the whole operation, the whole transaction from start to end. If you don't know all the commands, it doesn't work. It's not practical. So optional feature, nope, that will not work. The advantage though of, I can still do hardware, I still want to do some hardware, SPI and SPI and SVD. The advantage of this PSOC is that, well, I didn't implement it because I didn't have the time. For now, I spent 3 weeks only implementing all you've seen. But you can have shift registers and clocks. So what you can do is re-implement the SVD and JTAG protocols just using shift registers and the clock and the counter. And this is doable with the PSOC. They also have some, I think, universal data blocks where you can even implement some state machines and so on. So I have no doubt that it is possible to configure the hardware to do really fast SPI and to do really fast SVD and JTAG without using the SPI peripheral. So I'm confident with that. I don't need to test it. So the parts, so now everything implemented. I know I've implemented the firmware, all the features kind of I wanted are here. There are other features which I didn't implement, is detecting the SPI, but I know this will work. We have here an SPI. I've tested here the SPI output and input, and SPI speaks perfectly. So UART works well. Why shouldn't SPI work well? SDEMMC, it's also different. It's also not. There's no SDEMMC peripheral in the PSOC, but again, you can work with shift registers and counters, and the shift register and counter are pretty generic. So I can also speak eMMC, SDIO on these pins using the shift registers. And now my proof of concept for the IOVoodoo worked with this board. And yeah, we also almost spoke 1 hour. But at least I now know that this works perfectly for a need. I can have, again, the need. Being able to 1.5 volt to 5.5 volt GPIOs works perfectly. Analog routing, so I can scan the type on each channel, works perfectly. Digital routing, so I can use hardware peripherals to speak the protocols really fast, because I don't only want to scan the interfaces, I want to be able to talk to them and act as an JTAG adapter or an UART adapter or an SPI adapter for dumping memory and reading memory. This proof of concept is here, so now we can go back to the state we were 4 weeks ago and start drawing the schematic and have the adapter board. We could also, so this has, it is not, we could have a prototype using just this development board. It is not ideal, but it does work. So what is not ideal is that here I connect the target voltage, but the target voltage is the same across all the ports, but I want to have one port which is always enabled. So for example, the LED can be working, the button can be working, and the USB can be working. This port doesn't allow you to have multiple voltage domains on the different ports. So we have to design a board which does it. And also I want to design a board. I simply want to design a board and have a kind of professional tool. So let's start. I've presented the project, the status, and why I switched to this. I also looked to different things. For example, yeah, on the I told you something wrong. So where's the board? I've talked about the new RPI board from Raspberry, IPI 2040, something like that. I was wrong. You cannot put any all the peripherals to any of the GPIOs, only to a couple of them. You cannot also route all the analog domains to any of the all of the GPIOs. Now, the ESP32, you can route almost any of the peripherals to any GPIO. That would work. The problem is that only 3 volts you have, and because you have plenty of channels, you also need shift registers to control the voltage shifters. That would work. That would be probably less expensive and a lot easier, and you don't have to use a Windows tool. But now that I've started using this one and it perfectly fits our needs, I will continue using the PSOC, even if it uses a Windows software to compile everything, or at least to do the analog and digital placement. I think compiling the firmware, if it's just about the source code, could work without PSOC, although I didn't try it. So that was JTAG. Now let's try to design the boards. Designing the boards, let's use another screen. And now we will start designing boards. I've already, I think 3 weeks ago, I showed you how I create my parts. I don't trust any of the libraries. I create all the libraries for the parts I require, except for, no, I do. So, data, projects, IOVoodoo, IOVoodoo, and we're going in hardware. Yes, that's the right directory. I need to add some parts I need to add. I'll just cut. Now, let me increase the font so you can see something. What parts do I have in there? Yeah, the old parts which we don't require. So we can remove them. Del, I think. And we remove these parts. How does it work? Add, reset. I don't want to reset because it removes everything. You cannot just remove one component. Yes, you can. We don't need this microcontroller. We don't need the level shifter, and we don't need the shift register. So all the parts we've designed before, we don't need them. We will add library microcontroller. Now, there is a shortage. So, about microcontrollers, let's show DG key PSOC 5. I didn't write PSOC 5 correctly. There is, you probably already know, but if you watch it in the future, there is currently a chip shortage, and we have piece of microcontrollers. Yeah, I cannot source all the parts. For example, this is using which one is it using? Here we have the part number CY, like Cypress, although it's been bought by Infineon, 8C8 because it's the PSOC 5LP family, and then 888 LTY. Problem is that this doesn't exist anymore. So PSOC, we want one of these PSOCs. Yeah, apply. Now we want quantity of 1 because this is just a prototype. And if we sort the price, by now the price, so you see, these are really expensive. This is almost not. So the curious part is, on this board you have 2 of these microcontrollers. You have 2 exact same microcontrollers. Yeah, no, not exactly the same, but you have 2 of the microcontrollers. For example, if we look at this one, C8, C5, C88, let's find it, 888, this is this one, but in QFN. LTI, why is it LTI? It's this one. You see that one part costs 19 euros. It's very expensive for a microcontroller, but at this point I've spent already 3 weeks, but it does the job. It removes the need of having analog multiplexers, it removes the need of having shifters and level translators. So in the end it's the same price, although it's very expensive. And what's curious is that you pay 19 euros without taxes for this microcontroller. You have a second one which also costs the same price on this development board, and this development board costs only 15 euros. It's almost easier to remove the chip from this one and so to solder it on the other one, and costs less money. It just costs more effort, and it is not production ready. So you cannot ask for removing something in a production line. So it means that this development board costs, they don't make any profit, I think, out of this development board. Or if they do, it's very, very low profit. It's really meant to give it to you almost for free, and you can play with it. The schematic is good. I like this development board. The schematic was good. It allowed me to do everything I wanted. It has lots of peripherals, lots of components which are already populated. This board is quite good. I recommend this PSOC kit for 15 euros. Good documentation. The quick start guide is good. The schematic is good. It's quite good. But back to our components. We want kind of have the smallest available one. And the problem is that, sure, we could use this one, which is just 5 euros, and it is good enough for what we need. The problem is that we have a shortage. There is no parts available, and the least expensive part which I found which was available is this one. For a prototype, we will use this part, and I already bought one, I think. Let me check parts. Yeah. So this is my inventory, and if we look at the microcontrollers, we see, so this is the PSOC 3 series, PSOC 5, yeah, 5467. Is it this one? Yeah, 5467. It is still available. The advantage of this one is that this is a QFP package. It is a lot easier to solder. So for the prototype, I want to solder by hand. If I want to do any kind of high volume, because this device is requested a lot, I don't know, I have no one which knows about this device and requested, I will use something like this. It's like 5 euros. No, not this one, because this one is obsolete. I don't want to start a new design with an obsolete part, because in 5 years it probably will not be available anymore. I will use something like this one. C8, this is probably a bit too light. I don't know. We need to try out. It could be this one or this one. I want to use a QFN. Why not use a QFN part? It is a lot smaller, And if I do production, it will be reflow solder, and reflow solder works pretty fine with QFN. Just hand soldering is a pain. Could use something like this. It is still active. It probably has enough of the things I want, but I don't know. For now, I have this part with what's available. There's still a couple of them available, and we will do the first prototype run using this part. So we will add this to a project, MCU and Cypress. It's YAML, but it's heads. Yeah, variations. And so let's add this to a library. MCU and add, because there's several forms to this microcontroller family, we want the TQFP 100s, and this should not be a minus, it should be TQFP 100s. Seems to work. So this is the microcontroller. We want a USB connector. Less library connector, I think, and here we have plenty of USB connectors. I want to use USB-C because for data, why not? Reverse. USB micro would be fine. We want to use some USB-C. So here we have 2 USB-C, 3 even USB-C. Devices. Let's look at all USB-C, what they are telling us. Oops. Which one do we want? Because if I have the library, it means that if I wrote the library, I already have some parts available. This is a receptacle. This is what we want. We don't want a plug. So we have different receptacles. We have this receptacle and this receptacle. We also have data sheets for them. Why do I have 2 of them? Receptacle. This has 24 pins. How many pins does this have? How? Damn it. Open link. Ah, it opens the data sheet. This one is through hole. I think I want through hole and not SMD. And this one no, has all the pins. Yeah, the 24. It's not only through hole. The first pins are through hole. The back pins are SMD. And what's the difference with the other one? Let's open this data sheet. Oh, and no, it's not a link to the data sheet. This one, the same. Why do I have 2 different ones? Okay. I don't know why I have 2 of them. The footprint seems to be the same. You see at the right side. Ah, no, it's not the same. No, it's not. It is the same. They're compatible, and this is kind of a standard USB footprint. I want connectors. I want through hole because on connectors, particularly if you have something reverse the ice, you will always connect and disconnect. So we can use any of these parts. Let's try to see if so. This is the first. Let's try to see which I still have in stock. Connector. Ah, I didn't put them in my stock. I didn't add the USB drawer in my stock. But they seem to be really compatible. 24 pin, and this is also 24. Yeah, contacts 24, so they are the same. That's weird that I have 2 of them. You can also use 16. Actually, they're probably even cheaper. Let's try 16 pin. We don't need all of the 24 pins. There are with USB-C. You have different variants. Let me show you. USB connectors. You have all 24 pins. You have with 6 pins. With 6 pins, this is only for meant for power, not for data. And you have 16 pins. and 16 pins is the light when you don't need USB 3, you don't need DisplayPort and things like that. You can use a 16-pin device. Oh, what? LTSC has an issue. Doesn't have any connection anymore. Waiting for cache. I do have internet though. Ah, what I did, yeah, it works. I could optimize something, but it's okay, it works. Okay, LCSC doesn't work. Let's use one of these parts. I would like to use one of the 16 pins parts because they're probably easier to solder and have less holes. Then I need to add my library. This is the plug, yeah, 24 pins edge mounts. I don't have any. Oh, that's a shame. USB-C, micro B, connector, XH. No, I don't have any micro B. Micro B. My NEC with 16 pins only. Here. Type C. Apply. Damn, LCLC is slow. Add sort by price. I don't know what smart filtering means. I don't like when people are doing smart things instead of me. This, exactly. So these are, let me check the 6. So these are the 6 connectors. See, you have 6 connectors, but this only allows you to draw power. It doesn't allow you to have data lines. And after that, we have exactly the 16 connector. And this you can use for data. Still, yeah. And I think USB-C will not be available on all devices simply because even the cheapest costs 30 cents. On micro USB, you pay less than 10 cents. For a micro B connector, you pay less than 10 cents. So with the prototype, let's use the connector we have. So this is this is the 16-pin version. And this is good because it can be surface mounted. So you have holes, which makes it a through hole, kind of a through hole component. But the most important part is that these pins are soldered. You can do using this in reflow. And for these holes, either you do hand soldering, but you don't have to. You can actually use something which is a paste in hole, where you can still use the solder stencil and have enough paste going in the hole so it kind of connects this device. It's not ideal, it works. We will use parts we have, so we don't need to reorder new parts for now. Maybe I'll change mind and then change to this connector, because why not? But for now, let's start with using our parts. So we will use this receptacle. They probably almost are the same. Yeah. Oh, this receptacle. Let's use this one. Okay, and we only have one footprint for this. So we have the USB receptacle. We also want buttons and things like that to have library, mechanical, 6mm button. I want one button so I can switch to the bootloader mode. The 6mm button, I have plenty of them. They're standard, they're huge, but this is just a prototype and this is through hole. You want the least amount of through hole components when you do production, because through hole you pay for edge joints like 20 times what you do for surface mount. So you want SMD buttons, and for buttons SMD will be pretty fine. For now, it's just a prototype. We will use the buttons I have, which are robust enough I can solder them by hand. So let's add this button. Add mechanical and this button. Add this to library. We want to add library resistor. We want to add resistors. We only use the 0603 resistor. 0603 being metric, imperial, not metric. I think it's 2012 metric. So we have this part. We want capacitors. Capacitors, again 0603. Capacitor, that's added to a library. That probably so. It's probably the rest of the stream will be only drawing a schematic. It's probably not interesting for you. It might interest because I have a very exotic setup in how I draw schematics. I don't use Eagle. I don't use KiCad. I don't use Altium. I use something which is very unknown, which is not known a lot. At least not a lot. And also with this library management tool, Keda, I don't know a lot of people which has this kind of combination, so it might be interesting for you how I do my schematics. And at least I presented it once, so everyone which asks, how do you do schematic, I don't have to explain the whole thing from beginning. I can point to this video. We want to add one LED because we want to indicate things. Having LED is always nice. I think I've put it in diode, didn't I? Diode, TVS, no. Display. Although it's not a display. Display OLED, so no, I didn't add any LED. Transistor, TE, what is TE? What is TE? We want add. This is a fuse. We want to add a fuse, so let's add this part. But I don't, thermal fuse, I don't know what TE stands for. Why did I add to TE? Maybe a manufacturer. We want to add a fuse. Up for the USB input. I will make this is a reverse engineering tool. You don't know on which target you want to add, so I will add plenty of precautions and securities to the input and outputs. I don't care at this point with costs. These small devices don't cost a lot of money, but they add plenty of protection. And I did try some boards, and I would like it to have really good protection, and this didn't. And the boards I used didn't have protection and didn't prevent me from trying other boards. I don't want that. It's meant for a reverse engineering tool to connect to multi-thousand euro or dollar boards, and I don't want my adapter to fry the other boards, and if possible I want it to be safe from other things, so we will add plenty of safety. And the fuse is one of them. To have ferrite beads, dev board, capacitors, connector. It's weird that I don't have any diodes. Library, that I don't have an LED. Well, we can actually we can use any footprints. We can use the capacitor footprint. We will use a corresponding footprint. Library, diode. We can add. We will add some. So these are TVS diodes. This is to protect input and output, and we will add that. And I'll explain the difference between the two of them. Keda, add diode. And we will add this one, which is the one with 2 pins. This one with the one with 4 pins, or four data lines. What else do we want? Ferrite beads. I don't have any ferrite beads in my part library, do I? No. An oscillator. So, if you look at this board, you don't find any crystal oscillator or crystal resonator or something like that. It uses the internal RC. This is only 3% correct. It has an internal, I think, 3 megahertz clock. This is only 3%. For now, I had no issues. No issue with USB, no issues with SPI, and so on. But they are not very precise. If you want to have good instruments, you add an external clock. Here we will add an oscillator. So, or at least we will add the footprint to it. We don't. At any point, we could just don't place it, but at least we have the footprint. Library, oscillator, yeah. And I think this has either surface mount or not surface mount variants. Yeah, SM is surface mount. Which one do I have? So let's look at my parts. Where are oscillators? Passives, SM, here. US, this is, so I don't have any picture, but these are the quartz oscillator which you find on plenty of boards. So, let me show you. Actually, oh, that's weird. Yeah, there are so many different. So these are two. Regarding oscillators, let me show you the different variants. Here, you have these huge crystal oscillators which you find on all designs. They are very, very inexpensive. The problem is that they're huge. We don't care about huge for now. This is just a prototype. What we could do is have, like on this board, and now they are getting cheaper, this kind of oscillator. They have 4 legs instead of 2, but 2 of them are ground. You also find them with only 2 legs. They're, you see, they're compared to this, they are 1/5 of it, and they're surface mount. So this also exists as surface mount. They are only 1/5 of it, and if we do a production, we will use one of these tiny things. I don't have them in stock, but I have plenty, really plenty of these surface mounts in stock, which you see here. I still have 43 pieces left of this surface mount clock. So for prototype, we will use this. In the end, we can still change and again use something like this. This is also an oscillator. But for now, we will add this one, and we have it in the US. And this did I have? So let's remove this data sheet. Let's remove this one. Let's remove this one. So okay, US doesn't work. I think US is S is U. Let's have a look. Fin SM S radial crystal pattern radial housing pattern crystal. Okay. So the difference between the U and the S is the height. Probably the U is very high. We see it here. Yeah. No. What's the difference? Height. Yeah. See the height? This is a huge oscillator. I don't have any in stock here. I don't have any at all. These are really high. Now, this is the normal one with through hole. We want the SM version, which is the surface mount version. It is still as high, but instead of using through hole, which you see radial, we use surface mount. So we want the SM version. So and at SM. So we don't have the LED for the schematic. We don't need the LED because we can use the normal LED symbol. For the footprint, we will add the correct footprint. For now, we almost have all we need. Rake library. Now it generates all the patterns and all the symbols for all the things we want. And now we can start. Did I start? No. Touch IOVoodoo.ch, and now what am I using for schematics? I am using Lepton EDA. Probably never heard of it. Did you? Lepton? Lepton EDA is the suite. Lepton schematic is the one we want to use. IOVoodoo. And this is a fork of the Gida Shem. And Gida Shem doesn't have a lot of development. It's kind of stale. So they have forked it, and now it's Lepton EDA. Fork it's called Lepton EDA, has lots of progress. It's the first time it's running since I've reinstalled it, because it is changing a lot. So it is currently being developed on, so you have to use the Git version. And if I install the Git without reusing it, this is why it needs to compile some footprints and so on. I hope it works though. I know what I also need to add. So IOVoodoo is it here? No. IOVoodoo library, Veda, symbols. No, it's not. Let me add it off camera, so I don't have to show you all my things. We can update this. The part we use PSOC 5. No level shifter needed. (1.7 to 5.5 volts). Channel voltage range. It's this 1.7 to 5.5 volts. No level shifter needed, because it is the PSOC can already do that. One ADC. We don't need an analog multiplexer. No, now this is Lepton EDA. Let's switch this here. No analog routing. Analog. Multiplexer needed. Analog routing in MCU. Then we have, so bit banging, we don't need any level shifter with direction. This is what we, no level shifter needed, and we have a 16 channel so digital routing in MCU. So we don't need a level shifter. We don't need a multiplexer for the hardware peripherals, because we have the digital routing. We don't need level shifter, we don't need a shifter register, because since we don't need to control external libraries, external parts, we don't need to drive them, we don't need a lot of GPIOs. We do everything in the analog and digital routing within the chip. Current part library, we already have it. So now as current, so proof of concept firmware. That's okay, that's done. This is work of the 3 weeks work since the last stream. Current task, schematic. This is updated. So I need to, I know I've added here library, okay, symbols. There's one symbol I don't generate, I've created it by hand, and this is the title screen. So here, this is Lepton EDA. Now, I I need to restart laptop media. That's one of the pain. You need to restart every time you change the library because it doesn't remember the library. So normally if I add library or add components or L, we find the title. And let's start with some good documentation and the title. Hub. And we will often close and reopen it. The mouse has a bounce back. That's a pain. Title. IOVoodoo. Author King Kevin. Without that's the pain always. I don't have a keyboard which allows me to add the accents, so I know there are some alts tabs and so on, but I have my name here, so I will just copy it from here. Organization. Oh, it's not really an organization, but IOVoodoo. The dates. Let's start with today. We will change the dates to when we send the production. For now, it is today, 05/25. Version, this will be auto-generated. Version will be auto-generated. License will not be auto-generated. And I think it's open hardware license CERN or CERN open hardware license S, something like that. Oh, I don't remember. So previously I used the CERN open hardware license 1.2. Now there's the 2. CERN open hardware license version 2, and I want to use the with reciprocity, strong reciprocity. It's this one, CERN P. CERN's open hardware license P, and P means that any part of the things we are using will force you to also put your work under this license and keep it open. It's something like GPL for hardware. There are more permissive. For example, I think V means, no, S or V, I don't remember exactly. That's wiki. There are 3 of them. That's version 1, that's version 2. Yeah. S is strong reciprocal, meaning any part you will use of my design, if you use it in your design, being it the schematic, or the hardware layout, you will need to put your project under the same license. Weak reciprocal mean if you're only using my part, you have to keep my part under this license and keep it open and keep it public. So if you're shipping a device, you have to put my part available under this license and keep it open. Then we have the permission variant. This is something like BSD. You can do whatever you want. You just have to, you can change it, you can include it in your board. You just have to mention that you got it from here. Okay. And we want the strong. Strong is S. P is permissive. S, yeah, strong. Close. Now I have, why do I have, okay. That's done, yeah. Version and revision. Version is actually in here. That should be 0 for now. No, it's not version 1, it's version 0. It's a really prototype. And the revision will be calculated using Git. And every time you do a change on the schematic, the revision will, the schematic only, the revision will be incremented by 1. This allows me to count how many changes I made and to know if the schematic is a bit newer or not. Don't remember if the date is auto-generated using the required. Don't care for now. So let's add the parts, and the parts are, we want our device, we want a fuse. Actually, is there another fuse symbol? Fuse. Yeah, it looks more like a fuse. Yeah, I know one is US, one is EU. So we can use all fuse actually. It's the same than the connect one. So no, the basic device, all device. We want a fuse. We only want one. This is for the V5V USB input. I know what we didn't add. We'll add it later. Oh, we can add it now. Resistor. Yeah, resistor. I don't use the symbol. I only use the footprint. Like for the crystal. Because I prefer the US version of the resistor, which is wire wound. Now resistors are the chip resistor are not wire wound anymore; they're laser trimmed. But I think it's readable. So we will add for the fuse. We will also add this logo, which I find a bit old. Just the other one is also perfectly fine. It's up to you. I find it a bit more readable. We will add. So we don't add. So these are the level shifters, we don't use them. These are the shift registers, we don't use them. We use a button, but I don't use print. We have capacitors. Capacitors, I only use non-polarized ceramic capacitors for this small project. No tantalum, no electrolytics. It's not high voltage. We have so resistors, we have capacitors, we have LED. LED, we use the symbol. We need our USB-C connector, which there we have to use our device. It is, oh, nice. We want IO2, I1, IO2. Actually I should add it that the input is on the left. Yeah, the input. Oh, it is actually IO. That's the input, that's the output. Yeah. So these are TVS. This is to, wow, it's huge. The symbol drawing is huge. This is to protect the data pins for USB and so on. But we use, which one do we have? SC, I think it's the small one. No, we don't. The symbol is the same, but the footprint. SOTS. SOTS, I think. Yeah, I think we use this one. So we have the footprint. So the footprint is already matching, and we will have this one for the footprint. So this we remove. That's the USB-C. You don't see that this is USB-C, but we will change the name. And we want to add the microcontroller, which is not the STM. Didn't we add it? It's not there. Oh, I'm blind. Huh. What's the microcontroller? We do add it. It's probably because this footprint doesn't exist. Let's check the footprint. So TQFP, not minus 100, but just 100. QFN. Here, TQFP 100. That exists. So this is the schematic. So the schematic should be there at housing TQFP 100. Why didn't you create it? TQFP 100. Do you complain about something? Yes. Rake file. The project is not USB cable tester. This is another project. We have IO. So the rig file allows me to manage my library and export all the fabrication outputs and all the schematic outputs. So this is also why I don't use KiCad, don't care, because it didn't have, at least when I stopped using it, it didn't have a command line interface to export the schematic as PDF or export all the devices as Gerber. You always had to go through the menus. Yes, there were some scripts which were existing, but I think it was just for the hardware layout, so the board layout, but I want to have something which is designed with this in mind, and this is why I use this one. So, does it complain that the symbol is not existing? It is reading this, and it is generating the symbol, so the symbol should exist. Okay. Let's start again, Lepton. Components. Ah, here it is. I don't know. Oof. Too many ports on the left, on the right side. I could add. Why don't I have P15? Is P15 not defined? Oh, I have issues. You see P06, and yeah, I didn't verify this footprint. I just created it, but I didn't verify it. And you see, I have an issue. P06 and P36 have the same pin. That's not possible. And here, yeah, there's a second one. So this footprint is wrong, and also I think there is a P15. So let's fix the footprint. Again, let me get the data sheets. This is data sheet. We have this family. Pinouts. This is QFN. TQFP 100. It's this one. So P36, here it says it's 51. P3651. Is it the case? 51 P36, yes. So P06 is wrong. P06 should be 78. Footprint, where are you? Here. P06 78. Okay, there's something wrong. This is correct here. It is 78. Why are you telling me that P are using P03? Ah, sorry, P03. This is the one which is faulty. P03, it's 74. P03, yeah, 74. That should be 74. Let's double check. P03, 74. Yeah. And doesn't it have port 15? Yeah, port 15, it's here. Why isn't port 15 drawn on the schematic? So, schematic here. Ah, typo. Port 15 should be on the left. So, we'll move this symbol. We need to regenerate the library. So this is kind of a pain. I always have to regenerate. Okay, there's something wrong. It tells there's something wrong in the beginning. Ah, yes, this doesn't exist. LHT is the board layout, but we didn't create the board layout, so yeah, that's okay. And gits, we didn't start gits yet, so we can start actually git init up. Now this is created as git. We can version it, and we should add the sub module for the library. We'll do that later. Or do I have the command? I Submodules add, yes. It already exists in the index. So what? Can't you just put the submodules as it is? MV library library.back. Let's do it this way. Vim git config submodules library. Oh, okay, it's already there, active true. Okay, that's fine. The submodule is already in there. Now we should have the right components. Let's go. So we don't need this anymore. And add components, or L, faster. Here. And now we have 2 ports. We could add a 3rd port. Nah, it's fine. It's huge though. It is 100 pins. It is huge. So I need also to open the data sheet of this device. Let's open, 2 things. I didn't draw any data sheet, any things with that yet. So let's first from left to right. That's the USB. So USB, we will name it, that's the part number. Add attribute value, the value will be USB-C. The value is not shown. It should be. No, it is shown. The value should actually be this device. Yeah, this should be the value because this is the part number. Value. Okay. And this device would be USB-C. And now we can switch up. Add USB-C here. And because it is a connector, it added J. So P and J are 2 reference designator names for connectors. I don't know when to use which one. In this case, it will be J. How does USB-C work? We have here data plus, data minus for USB. All the other ones we almost don't need. We need the ground symbol. Ground. Up, close, and we needed a lot of pins. Shield. In USB-C, there's a huge debate. There's plenty of possibilities how you treat the shields on USB connectors. You can either directly tie it to ground, or you can leave it floating, or you can add some kind of filter, RC filter, where you have a 1 mega ohm capacitor and 1 mega ohm resistor and a 100 nanofarad capacitor and this kind of filter. For USB-C, it really doesn't matter because in USB-C, in the connector, let me find it so I can prove it to you. The data sheet for USB-C. Data, where is it? Electronics, USB-C. Well, let's look at the specification. This specification. Let's have a look at the cable assembly. So that's here. Cable assembly. This is USB-C. If you look at USB-C, you will find that the shield has this pin, and the shield is must be connected to ground, and all pin ground can be here. This restriction. Shield and ground shall be connected within the USB-C plug on both ends of the cable assembly. So in USB-C, you don't have to ground. You can ground the shield if you want it. You don't have to ground the shield, but you have to know that it will be, the shield is grounded. So that's done. So that removes any kind of thing. Otherwise, I generally leave it floating because the host side does the shielding and you don't have to do the shielding on the other side. So here we will do the same as I would do for micro P. I will just have no connects to them. Library in and C, no connect bottom. I will use this symbol. Close. We will not connect USB-C. VBus. This will go through the first through the fuse, then through the ferrite. And this will become, we will have plenty of power rails. We will have 4 power rails, no, 3 power rails. Power rails. The problem is, do they have other devices? Do they have other things? I don't like the one with the bar. I like the one, but it doesn't exist, does it? Or it points up. No, it doesn't. Damn it. Do I have to create it? To create it. I want the one with the arrow on top. It doesn't exist. So we will use 5 volts. We will count this as 5 volts. Afterwards we will have plenty of others. We will not take care of it now. We will take care of it later. But first it goes through the fuse. Then it will go through the ferrite to remove any high noise from the USB. Then this will become of 5 volts. Oh, not line. Damn it. Net. How was it? Oh, it was net. Yeah, net. All the V-bits, they're also in the cable, they're also I think you don't have multiple cables, you have only one cable, but you can use all of. So this is a fuse, and the value would be, so this is the name of the fuse. 500, do I have some? Let me check in my parts. Passive fuse, I will use glass fuse, no, this one. Resettable fuse, 500 milliamps, because, well, on USB-C you can draw more than 500 milliamps, but we will just use 500 milliamps fuse. Actually, 200 milliamps fuse could also be enough for a device, but we want the user to be able to reuse the 5 volt pins. So we will add the 500 milliamps fuse. That's good protection enough for now. So we will add the value. Value 500 milliamp. This we don't have to show. This is the footprints. We don't show it. It's just a 500 milliamp fuse. And if you look inside, you know that it uses a 1206, again, an imperial footprints. Ah, sorry, wrong fuse. I will use this fuse. Let's okay, here we add the value. Up. How is R redo? How is not undo? Redraw the line. Add attribute value 500 milliamp because USB-C is able to at least give 500 milliamps. And this is now our 5 volts. Up. Now, for USB, we will not use these TX plus, TX minus, SPU. This is, well, I think it's for debug or audio, and this is for USB 3. What is SPU for? Okay, but we don't need it. We only use T plus T minus. So we will add no connects. NC rights here and NC left. So we will not connect these pins. No connects. We don't need this one. And how I do the schematic is from left to right. Left is the input, right is the output, top is voltage, ground is, bottom is ground. SPU, amp. And now USB-C is, you twist it, so you can have the other one or the other side. And depending on the switch, we only want one USB, so it could be on one side or the other. Because we don't know how the cable will be turned, we connect both of them, so we don't care on the other side how it switches, or if the cable has only one lane, which goes to this connector, these will be connected. These, both sides of the connector, they're called side A and side B, side 1 or side 2 here. They will be connected together to form USB plus and minus. Generally I add, and I will also add, I don't know if it's in the design recommendation. Let's have a look. So let's connect them together first. Nets, we will add, for that we'll add a net name because it's not beautiful to have these things connected together across all the things. So we can add attributes. The net name will be D plus for this one. Add attributes, D minus. Actually, I think I don't remember in USB. Sometimes it's D plus right in here, and I think in USB-C now they corrected it, and in the schematics it's DP and DM. Let's have a look at again at the USB-C specs. Here you see DP and DN. Previously it was the plus. Now the signal names are small p and small n for USB-C. So we'll use it this way. Either way, it is perfectly readable, but let's do it this way. They use N, I think. D negative, positive and negative. Same here. Net up. Net. Add attribute D positive. D negative. Let's have a look. So before we connect it directly to the pins, and we have to find out which pins it is by looking at the data sheet of this microcontroller, I want to add two things. Actually, I want to add two things. This thing will protect, TVS will protect from too high levels on the I/O pins, and will also protect ground and V-bus if it's not too high, and ground. So this is kind of an input protection. So we will add this to USB. USB is not finished now. Let's finish the connector. Let's finish the USB connector before we go forward. This we don't need for now, and we'll not need it immediately. USB-C is reversible, so you have to indicate which side you are on, so the host know how to switch the signals. And USB-C, to tell which signal you are, you just pull the CC pin to ground using kind of a specified resistors. I think it's called RP or RD. Yeah, I think it's called RP. Let's just have a look at the legacy cable for USB-C. For example, this is USB 3, we don't want. USB 2. CC, see note 1. The CC line, note 1, is connected. That's not the right one. RP 555. I remember it is 5.1 micro B. It is 5.1 kilo ohm. Now I remember the other one. This value, type C, RP, exactly. It's called RP. You can have several measurements. I think 5.1. Let's go to this table. It tells you so the pull down resistor doesn't only tell you which way the connector is connected, but it also tells you how much power you want. And if we look at this table, we see that 5 default USB power. Sorry. Now, okay, I get it. This is the source. On the USB side, we are the device. Here, on the left side, USB A, this is the host, and the host needs to pull it up and this side. So this identifies the host. We are the device. So we use, for example, for this, the host will be on the USB-C side. Our device is kind of the USB micro side here. And on the device, it's RD. RP is for the host, RD is for the device. And here it is 5.1. And there's this table which tells you the resistor down to 5.1. If it's precise enough, then it can have power capabilities, and you can have plenty of other things. So we need 5.1 kilo ohm on the CC line. This is RD, and we will call it RD to indicate that we are a device and that you provide power. Without this, it will not detect that we are connected, and it will not provide power. We need the power. So 5.1, this is where we see it. So schematic, we have 2 resistors. An attribute value 5K1. 5.1K, 5K1 is the same thing. Show the value. Yes, we want to show the value, and then we also want to add a note. Add attribute note, and we call it RD. So we know that this is the RD of the things, and we only want to show the value, the capable. Up, since we close it to ground, we will have it this way. Up. Now I'm just putting it the right direction. Up. And what I did is remarry it so the points, the text is aligned to the right. Up. We will have one ground. And since we don't care on which side it will be, because we are not using the multiple of the data lines, we'll have it to both sides. And here we reverse, we mirror it, and again now it is aligned to the left. You see the small dot here. This is how you do USB-C. Now, next parts after the input, let's go from left to right. We have the TVS, which is there to protect the I/O signals from two things, from electrostatic discharge and from overvoltage, undervoltage. And this is what the TVS will do. I can show you the datasheet so you can better understand what is it in the datasheet collection. Here, this one, it's almost the same. Here you see ground voltage, and there's a breakdown at 5.6 volts, something like that. So it is compatible. This diode are really fast, so they're compatible for USB 2. Up to high speed, we only use full speed, 11 megahertz, 11 megabits per second. It is meant for ESD protection, but it does more than ESD protection. So, and here you see the ESD protection. First, before we look at ESD protection, yeah, breakdown voltage between grounds and V-bus, so between 6 and 10, meaning my mouse has some issues with the up scrolling. If there are more than 10 volts on the input, it will short it to ground, or more than between 6 and 10 volts. So this kind of protects already the V-bus. Now the I/O lines also protected because if there is more than V-bus, it will go through this diode to V-bus, and if it's reversed, if there's less than ground, it will go through this diode to ground. And this is how this I/O is protected. And yeah, this is with 4 pins. We have the same with 2 pins. And this is what we have. So we can remove this data sheet. I presented it to you, and this is this called TVS. And they are very high speed, and they are there to quench all the high voltage. And it saved me. One of my streams is about DMX control board, and here one of these TVS saved the device from breaking, but this broke. So this is really an important part, mostly for ESD, but it can really save your ass. So we will have this data plus and data minus line connected to it. Data minus, data plus, and then before we add it to our USB, I add some inline resistors most of the time to prevent the ringing, to terminate the lines. 22 ohm generally. Can we see it on other devices? That would be interesting to show you what I mean. Data sheets. Doc, this is the schematic of the development board. Let's see if they add it or not. Here you see data plus, data minus, 22 ohm. So they also add it, and it is really recommended. On some times you don't have to add them, and they save you a couple of cents. I always add them. They're not bad as such, so they cannot do anything bad. Oh, here they also have a TVS diode to protect voltage targets. So voltage target is probably not higher than 5 volts. So yeah, we will add 22 ohm inline resistors. And this prevents ringing on very high lines for very high speed signals. So resistor. And we need to find, so up 1, 2, add attribute value 22R. We could also rename the lines now to USB, again, D plus or D minus, using other letters like huge P or huge N or huge M, D plus, D minus, and we can actually name them as so this is USB-C, we finished. This is the schematic from the development board. We don't care anymore. Now the data sheet from this device. we could call it how they call it, USB plus and USB minus, and this is defined, where is it defined, where the things are. Do I have to look for USB? Ah, here, D plus D minus 36, 37, and they call it D plus D minus, so we can call it this way also. How is it? Ah, here. P15, 6 and 7. And we see it also here, 6 and 7. Oh, they use the same I/O as SVD. That's where we also need the SVD port, but we'll add it just afterwards. So we will call it D plus because in the schematic they call it D plus. 15.6 is D plus. Net. We'll add a net. Net. And attribute, this will be D plus. D minus. 15.6 is plus, so we can copy this name. We could also connect it, but I prefer it. I find it more readable if there are not wires going through all the board. I keep the boards into sections. Since this is part of USB, we will add it to this USB, and this is not complete yet. It needs a ground and the 5 volts from USB. And this is too high. Up, and we will add a box or text on box. And we'll add it later. We could add it now. Is it finished? Yes, USB is finished. We will add a box up. We can modify the boxes afterwards. We will add text. How do we add text? That's USB. Apply. Now we start connecting all of these pins. We connect them now as there's something more important. Yeah, we need JTAG, so we need a 4-pin or 5-pin adapter. Let me think. 5-pin, we need to also be able to provide to reset. Yeah, well, also we'll add reset pin. And we can have a look at again how they do it. And actually, yeah, it is fun because this is TQFP, yeah, SVD-IO is shared with it, with the D+. That's fun. So you cannot use SVD while using USB, but it makes sense, you only program them. So we have to fix this. This is called D-. D- is SV clock. Let me put this here so I don't have to switch all the time. And you can also kind of see it. D- is on 7 and that's SVCLK. Oh, they call it SVDCK. Ah, that's wrong. There's no data. Oh, for me, SVD-IO was serial wire data input output. Close, and this is SVD-IO. SV data input outputs. I don't know if we need the reset line. Yeah, I think you can only connect to SVD while under reset, and this is why the schematic for the data here, the schematic from the development board. Where's the programming header? Here. Oh, wait. The fuck? Okay, this is another chip, but here SVD is not connected to USB plus minus. Let me check in the other data sheet how they do it. Data sheets. That's the 58. We are pinout. Pin description. Yeah. Pin description. Okay, pinout. Pinout. Ah, that's weird. 4. What is 4? Do not use pins are do not use on devices without USB. Okay. But SVD, it's also here. Okay. So you can have SVD either on data plus data minus to save pins, because when you connect on the reset there is no data, but then you have to be sure that this is not connected to a USB device. Okay. But since we are connected on the USB device, we don't want that. So let's undo. This will be used as data plus data minus only. And for us it should probably be here. P10 is SVT-IO. P10. Actually I could add, now that I could add P1 also on the left side, because it's the control side. Then it makes more, yeah, I will do that, because P1 is most of the time control signals. What about P0? P0, is it control signals? P0 is a lot of op amp and so on. Yeah, I will add P0 and P1 on the left side. This way we will have 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, there will be 5. Yeah, let's add it this way. Up, and it will make the part tiny bit smaller. Bidirectional, yes, on the right side. So on the left side we will add P0, P1, and on the left side P2 to P6, and the rest. Regenerate. Did I quit? Yes, I did quit. Regenerate the library. White library. Restart Lepton, and normally, yeah, it is reconnected, but this is wrong. This is 5 and 6, and you already see the part is smaller and more readable. So SVD-IO on pin. SVD-IO is on SVD-CK. Let's call it how the datasheet calls it, because we already also do it this way. It's a weird name, but everyone understands when it reads it. So P10 is, did you add the net? Net's the clock line for SVD, as attribute SVD-CK. That's how they call it. No, it's SVD-IO. Damn it. This one. SVD-CK. So because it is here, we don't need to connect on the reset, but still connecting on a reset is probably better. How did they do it? So this device we don't need anymore. This data sheet here. Prog resets, it's on XRS. I don't know if in the data sheet it is mandatory to connect on the reset. I think because there are separate pins you don't have to, but yeah, having the reset is also okay. Prog reset, how is the programming connector? Where is it? Should be, here they also had a resettable fuse. They also have a protection for reverse protection. I don't have They really expect that the USB is fine, it's not connected to. If you have a problem on USB with voltages, then it's your fault. And here, you see, this is what I meant. And they only 10 microfarads, 10 nanofarads. This is what I mean with this. The shield is the chassis and the ground. 100K, 1 mega ohm, as you wish, and then this with 100 nanofarads or 10 nanofarads. This is one way to shield it and suppress the high noise and so on. You don't have to with USB-C because it is connected internally. Programming header. This is the programming header. Voltage target. In our case, it won't be voltage target, but do we make it 3 volts or do we make it 5 volts? We make it 5 volts. So we will connect it to 5 volts. And yeah, they also did connect the program reset to the reset line. Yeah, program reset to the X-res line. And this is also what we want to do. Do we need to pull up X resets? This is a good question. RST, just call it RST and not X reset. RST is a tiny bit more common. Do they pull it up or is it internally pulled up? So X reset, it's here. Why is it? I don't see it here. Push button. No. Do we want a button for resetting? No, you can unplug and replug it for resetting. No, we don't want a button. This is useful for developing. For not developing, we don't care. This is ground. X reset is not connected. I think there's an internal pull up to X reset. So it is active low. Here it is pulled up. X reset. It is pulled up and it is, so when it is high it doesn't reset and it is active low. So when you press on the button it goes to low and this forces a reset. This is the 99% of the cases reset is active low. Oh, they also add a TVS diode on this programming connector. Let's have a look if it has an internal diode or not. The data sheets doc. There is a digital design. No, this is not what I want. Hardware design consideration for PSOC 5. This is about VDD. Do they have sign? Okay, no, they don't. This is VDD. Reset. Resets. No. See device reset. There's a category. Come on. The link doesn't work. Again, the link doesn't work. IO and device reset. Here they also add a pull-up. But there seems there's an internal pull-up here, PSOC, internal pull-up to VDD1. So we don't need a pull-up, an external pull-up. Reset, power on, when there's power, it pulls up on, so this is configurable. But if we want to have some ports, yeah, so this is important, this part. This is why it's important to read the hardware design recommendation. Remember that the reset setting is applied on the entire port, so it also affects pin. This is if we use another pin. But if we use reset, this is not on a pin. This is on a separate pin. You can have X reset also. Is it somewhere written here? Yeah. If you use X reset, configurable X reset on pin 1, 2, and this is where you can pull it up. But I want about the reset pin, device reset. So, dedicated reset pin. Not all the devices have a dedicated reset pin. So you can either use the X-res or you can use this reset pin. Optional. Programming and debugging, yes. Okay, X reset. Here they connect X reset directly without having the pull up. Oscillation, that's for later. We are not yet at the oscillation part. For now we are at the programming part. Bypass, stack, X-res. Okay, configurable X-res stack, so it's here. Yeah. For devices with both X configurable as digital input with resistor. This is if you want something. Special cases from configurable high reliability application. Digital input with the resistive pull-up enabled for high reliability application. Here. For high reliability and the application, leave 1.2 connected, unconnected, and pulled up. So you configure it with a pull-up, but you still leave it unconnected. But it still doesn't mean, do we need to connect with an external? I think we don't need to, but we can. Dedicated reset pin. Is it recommended? Programming and debug. Here they don't do it, but maybe it's a simplified. We will add the pin. We can still unpopulate it. We will add the resistor. If we don't need the resistor, we can still not populate it, and we can try it this way. So it's not very clear in here. So what we will do is just add the resistor to be target, and if we don't need it, we don't have to connect it, and we will add a node to it. Resistor. Close. Value 10K. Could add even more. 10K is the standard value. We could add 100K. Let's keep it at 10K for now. And we will add a comment. Nodes optional. But still recommended. For the programming header, we will add a normal header. We can actually feed it with 3.3 volt. It doesn't have to be 5 volts for programming. One USB is not connected. So header, we need 2 5 pins. 5-pin header, it doesn't exist, right? I hate this. Connector. 5. Looks ugly. That does the job. It's gone. Let's call it J like we call all the other connectors. Come on. J. And this will add attribute value. This will be the programming header. Prog. And it will be SVT. Let's keep it as it is on this board, so we can use this programmer. We could use any other programmer, but since we have it, oh, this gets warm. Since we do PSOC, let's try to make it compatible with all PSOC friends, so everyone which wants to reprogram can use this programmer. Pin 1 is voltage target, so this is 5 volts. Or 5 volts, although pin 2 is ground. Pin 3 is resets. We had resets. Pin 4 is clock. SVT CK. SVT CK. And pin 5 is SVT IO. Yes, it is. SVT IO. And now we kind of respect the pin out. So if you want to make a debug adapter, it's not too hard. We can read. Other attributes, nodes, how is it called? It's kits compatible, kitprog compatible. Kitprog compatible. I would like to have nodes in another color. Can't I? No, I can't. Programming is done. Now the complicated parts. No, not yet complicated. Microcontroller. We need to add a crystal. Why? This was in the beginning. So yes, this is the device. Yeah, this is the device family, but the value is a bit different. Other attribute value. This we will use the one we bought, which is, where is my Heartkeeper microcontroller? This one. One is corrected top left, yeah. Now both should be aligned. This was not aligned on half thing. Oh, damn it. Up. Let's save with FS. And let's add the crystal. So the crystal is really optional because it has an internal which seems to be good enough because they don't require it. And if we look here, it is also documented. Where is it? Here. You can add really high precision 32 and then use the PLL. This is also more and more microcontrollers are having a phase lock looped inside, which allows you to multiply the external frequency to almost any arbitrary output frequency. But I don't know if it is better to use a real-time clock, which is really precise over a long time, and then use the PLL, or if it is better to use here we have target. No load. You see, okay. Or if it is better to use an 8 megahertz clock. It really depends on the PLL, probably. We will use an 8 megahertz clock. Here, you see, no load. It's really not necessary to if you want high reliability, then you can add the target. I should have seen it from the beginning. And here again, no load. This is also if you want to have even higher. We could also add it to decouple it and to not have it wiggle around too much. Where is my capacitor? We will add it. We don't have to populate it. If we have issues, so the point will be I will kind of have this prototype, stress test it. If reset is not stable enough without it, I will just add it. But if it's good enough without it, then I will just keep it out. Value, and then they have two schools, either 0.1 microfarad or 100 nanofarad. I find 100 nano faster to read than 100 pico, than 0.1 micro. And notes, optional. Okay, this is done. In theory, if we want to protect all the pins, we should also have some TVS on here. Actually, I think I will do it. So on the reset, we don't care. But on the data line, I think it is protected enough. On the data line, we should add something. Problem is this will not be accessible. This should not be accessible to the user. This is only for the developer once he opens the board. What we can do is we will add some TVS protection diode on all the input outputs. There will be a lot on the right side. Because there are lots, we don't use the 2 pins part, we use the 4 pins part. And because we use the 4 pins part, what we can do is have these 2 lines also go through, because we will have 2 free. And do I want to do this? It is really a lot of protection, but we can compact, this way we can compact the things. We don't have 2 different diodes. Yeah, we will add it. We will have this. So, redesign. Plus minus. This way we can show off. Do they show it differently, or do they show it for USB? Yeah, they show it here. No, they don't show it here. Where is USB? USB. They don't show the resistors here, but I'm sure they have here. They show the resistors here, because you want the resistors, you want them as close as possible to the pin, which outputs the data. This is why generally you show it to this side and not on this side because this is where you want to show that. So we will also do the same thing. We will show it close to the microcontroller, indicating that we want those protection resistors for the ringing next to the microcontroller where they belong to. Yep. So now we have, they also go through this TVS. The routing will be probably a pain because we have one component and the voltage goes there, but it's still possible. Okay. That looks fine. Can even make it a tiny bit shorter so we can compact the design. Should be done at the end instead of now. Yeah. I want to rest my head sometimes. Up. Okay. And now we can add also TIO and clock to this TVS and also protect this pin. Again, this compacts the number of parts. We have 2 free pins, and this makes it a lot more reliable. Oh, a lot more secure for electrostatics discharge or for any kind of other connection. For example, if the firmware is not finished, there will be a lot of things. So it might be that I'm connecting the program while I'm connected to the target because I want to check something, and these TVS diodes will protect me from SD or some other thing. So it's not a bad idea. Let's keep it this way. Is this the right footprint? 46L? What is 46L? Ah, it's sub, so it's correct. And if we look at the footprints, yeah, SOT. SOT footprint is correct. The clock. Here the clock, on the device they didn't provide any clock, but I know there are pins for the clocks which are not populated. I know these ones. This is for the low crystal, but there's also one for low speed crystal, but there's also one for the high speed crystal. We don't need any real-time clock, so we will not have this kind of device. It's not there. No, it's not. Ah, yeah, we can also. Oh, they added already here before the fuse. Not a bad idea though. Let's do it this way also. I didn't do it. I had it to the other one. PPT. So that's the value. But how is device PPTC? Add attribute device PPTC. I think it's. I don't know. Everyone knows that this means resetable fuse. But yeah, why not add also 100 micro on the input? It is also optional because, but we need to put this higher. That's USB-C. We need to put it even higher. I only want one corner, come on. How do I select only one corner? We're still at the clock, so the data sheet were here in this data sheet. TQFP, where is the clock? It should be Crystal, yeah, Crystal XO, Crystal XE, and Crystal XO. I think these ones, 15.3 and 15.2. What did they do on this development board with 15.3 and 15.2? They don't have it. They don't have it. (15.2) and 15.3. Ah, do nothing with it. Ah, here. Ah, Crystal. That's the. So the same pads are for input and output and clock. Let's have a look. So let's have a look at the design guide again, which doesn't have any chapter marks in the PDF at least. I/O selection, device reset, oscillators. Here has an internal highly versatile configurable clock. No external for mailing design. No external crystal is required. Yes, I think for our design also it won't be required because we don't do very high speed protocols. The low speed protocols don't need a high tolerance. So the internal one, 1% can generate accurate 1% over voltage. That's good. But if you want really precise, and the clock, the ones which we do with high speed, we provide the clock. So we don't need to be synchronous because we are the master. So we really don't need an external clock. But if you need, again, here, yeah, what I say is quite accurate actually. For basic purposes, internal low speed oscillator is also good. And if you need greater system accuracy, you can use an external clock crystal oscillator. We don't have it on this board and it still works fine. I still add it because I want something which is reliable. 4 MHz to 25 MHz, we will use 8. Here for more information, see application node, external clock. Okay. If echo is not needed, pin can be reused. Yeah, pin selection. But okay, so it's not even there. Go to pin select. Damn it, this stupid devices, this stupid PDF. I/O selection. Here there's something missing. Megahertz or 30 kHz clock. If not, pin can be selected. But which pins are these? Crystal. Xtal. These are the pins. There are two. Kilohertz. Okay, now I get it. Kilohertz crystal. This is for the 32 kilohertz. We have a megahertz crystal also. Where is the megahertz crystal? Crystal. Megahertz crystal. This is 15.0 and 15.1. And we will name it 15.0 and 15.1. So we need a crystal. Crystal oscillator. That's the symbol up. Add attribute, value, we will add an 8 megahertz, but and attribute nodes, this is optional, 4 to 25 megahertz. And now we also need, so the picofarads depends on the, so the crystal also need external capacitors, and it's picofarad, and it's between the range 8 to 16. It always depends on the crystal, not on this thing. So that depends on the crystal. We will add something like, I don't know, 12 pico. I think I don't have any specification for mine, for the one I have, because they are cheap ones. Let's check. Where are my parts? Where is my browser? Here, parts keeper. Oscillators, surface mounts. No, that's not. If I look at the, I don't know the manufacturer, I don't know the parameters, I know nothing about this crystal. So it's between 8 and 12 picofarad, whatever I have at hand. Which one I have? It's not too important. And tack. That doesn't look nice. This is XE. How did it call it? XE. We don't have to add the name because the component is just next to it. But let's have it nicely there. Up. XE, XO. And 2 capacitors. Capacitor. Up. We can stretch it. So it's kind of aligned. Actually not to stretch it, so the text can stay far away. Let's define it, add attribute. We will link the footprints later on. For now, let's say 12 picofarads. We need a ground symbol. These are also optional. Nodes, optional. Optional. Net. I think I will still add them because I'm more confident using an external oscillator than the internal one. 1% is not too low, still high. And they're cheap. Starting to look nice. Now, all of these things, let's take care of the power. Power is always, yeah, these are all to ground, that's for sure. Then VSSA is for the analog, and what is VSSB for? I don't know. Maybe they're connected to ground, but do they need some filtering? Ah, I didn't need any ferrite bead. Do they have? No, they don't have any ferrite bead. You could add a ferrite. You could add a ferrite bead here to remove the high frequency of the USB, but I think this capacitor takes care of it. It probably replaces the high frequency noise. That removes the need of a high ferrite bead because you already have this component. That's nice. Yeah, I think. I'm not sure, but I would guess this is this way. How do they connect VSSA, VSSB? VSSA is also ground. Okay. What does VSSA and VSSB mean? What do they mean? Yeah, here we have VSSA, VSSB. So VDIO makes sense in the hardware design. I think they have here power should be one of the first power system. Yeah, I see power system is one of the big ones. Analog, VSSA is analog. VSSB, for the boost. Okay, B for like boost. We don't have, so this also allows you to have a voltage booster. So even if you have 1.8 volts input, you can boost it to 3.3 volt, which is quite nice. And we see here VSSA is all directly connected to ground, and VSSB also directly connected to ground, all connected to ground. Do we have another ground symbol? This is earth symbol. This is not ground symbol. We don't have, although we can name it ground. So this is the ground symbol. This is not 0 volt symbol. We have another symbol which is really for digital ground and not for earth ground. Power rails, generic ground, generic power, ground. No, I think I will create my own symbol for that, because this is generally earth, not chassis, not digital ground, but earth. We don't have earth here. So I would want to have the triangle symbol for digital earth, which is this one. Later, I will change the library later. So, what is important are the VDIO. They're always decoupled. And why does the D require a 1 microfarad and not 100 microfarad? VCC, sorry. VDD is for the VDD is also not why one require VDD. Here, okay. All the VDDIO 100 microfarad, 100 nanofarad, and all the VDDD or VDDA and so on 1 microfarad, except VDDAA, it's 100 and 1 because we want to filter different things. Analog regulator, VCCA. This is for the regulator inside, whatever they need, and also 1 microfarad. So yeah, we can steal this design. VDDIO. Yep, we can steal this design. Often is my schematic. Often you don't put the things here, you put them. The bypass capacitor, you don't have to put them here. You can put all the bypass capacitor on a separate part of the sheet because it makes it a bit more readable. Here, plenty of capacitors becomes unreadable. And I think this is also what we will do, except for the important ones. I don't know. If we add a lot of capacitors, it will become really fast unreadable. VCCA and VCCD, what do they correspond to? VCCD, that's the power regulator, that's the digital domain. And VCCA, that's the analog domain. Makes sense? Okay. Do we add it here so it's more readable? Less readable, but at least it's more understandable what I want to do. It also tells you which capacitor needs to go where. Ah, let's try it this way. If it's not too cumbersome, I'm sure it will be too cumbersome. If we stack all the things, yeah, it will be too cumbersome. But it means I need new power things. Yeah. Yeah, let's do it this way. Add attribute VCCA. Sometimes on the analog input you also even have Farad beats, but I don't think here they don't have Farad beats. Here they also don't have Farad beats on the VCCA. Do they? VCCA 1, 2. What is it here? VCCA. No, they only have decoupling. VCCA. Okay, that's done. That's all. That's all of them. Nope, they don't have any Farad beat. That's okay. So VBATs, we don't need the battery. We will not operate it with battery. So VBATs can be disconnected. Okay, it's not shown here, but we will just not connect it. And no connect. Top. Close. VBAT will be not connected. Actually, I didn't read if we can connect it to no connects or not when we don't use it, or if we need to take some precautions and ground them. Let's read it in the recommendation. VBATs. Okay, you show me the pin, volt input voltage. Yes, okay. VBATs. This is, this is if you want to operate with a small battery. Here you see, this is a good example. Boost converter, typical application circuit, the battery. You provide 1.2 volts, a single battery, but you need a higher voltage, so you can use the boost. It's nice. This PSOC is really, it's really versatile. You can use it for plenty of things. It is very expensive, but it is really versatile. And you can add VBAT to power the Intel Core probably, and then you can also boost it, which is quite nice. So you have 5.5 volts here. If the voltage boost is not converted, tie VBAT VSS to ground. And leave like inductor unconnected. So we needed to connect to ground. I wouldn't expect that. I would have unconnected these. But they say ground. So now it is really ugly because ground should be going to the bottom, and now this is not feasible doing it to the bottom. So it is really, it doesn't look nice, but what we can do is this should be left unconnected. And ground symbol. Ground should always go to the bottom. Now it doesn't. There are some exceptions. We still know it is ground. No, other attributes VCCD. What's the difference between VCC and VDD? Again, let's have a look at the recommendation layouts. Up. PSOC, up. Power system. Analog. still. But what's the difference between VDDA and VCCA? Ah, analog regulator. VCC, where is VDD? VDD, what is VDD? VDD. It's also for regulation, for internal regulation. I think this. VCC is for internal regulation. Yes, VCC is internally regulated, and we need to provide, and VDD is what you provide. Okay, okay, now it makes sense. So we also need to add 1 microbit only, although here VDD 0.1. But that's it, because it's the external one. For the internal, just only 1 microfarad is enough. For everything which is external, we need to also add 100 nanofarad. Got it. So VCC is internal. Let's add wires to all of them. Other attributes, VDD up, VDDA. VDDD. Attributes, VDDIO 0. And we need the IOs later on. Add attribute VDDIO1. Add attribute VDDIO2. That's not a 2. That's a 2. Attribute VDDIO3. Up. Cancel. Up. Up. Now we can make the bypass capacitors. So we need 2 of them. Add attribute value, we need 100 nano and we need 1 microfarad. We will need more of them for the voltage regulator, that's another part. Microfarad, which I'll talk later on. Okay, so VCC is always what is internal, it only needs 1 microfarad. So let's make it this way. Ground. Up. Up. VCCA, it only needs 1 microfarad, it doesn't need the 100 nanofarads. VCC, what is it called? VCCD? Yeah, or digital VCCD. Then we need the same for VDD. VDDA and VDDD, but they also require 100 nanofarads next to them. then the 4 ports also had 100 nano, also require 100 nano. 1, 2, 1, 2, 3, 4. This is VDA and VDDD, and this will be the IOs. IO0. IO1, IO2, IO3, and now we can connect the powers. So this is just bypass. We can make a box. Should generally place on the bottom because they're connected to ground, and everything which is ground goes to the bottom. So box here and text, bypass or decoupling, however you want to call them. Don't know if there's a difference between bypass and decoupling or if it's a different mechanism. Yeah, they explain different parts of the purpose. Now we can connect the things. We will have VCCA and VCC connected together, actually. But to make it clear, we make 2 different ones. But in reality, they are connected together. Up and the IO, this is a different part. Now the complicated part, or the complicated, we'll have a target voltage. What we wanted in the beginning on is a target voltage. And this is unconnected. Yes, this is just a net name, so we will leave it like this. Target voltage. This is the power domains, and we have to read the datasheet to find out the power domains. Here, these are the power domains. We need to provide power so it works. VDDD. Yeah, we can provide 5 volts even if USB requires 3.3 volts because it uses the internal voltage regulator for VDD. So this is fine. I didn't add any button and LED yet. On the board, dev board, the LEDs on port 2.1 and the switch 2.2. It doesn't really matter. We need 2 ports for the target voltage, for the target board. We could use 1 VDD, so we use only 1 domain. P12. Do we use something from P12? What is P12 for? P12, we use nothing. So we could use port 0 and port 4. In my board, I'm using port 3 and port 0 actually. Port 3 and port 0. We will use only this domain. For the target voltage, port 0 and port 4. Do I have really port 4 on my device? Not all the devices have them. For example, this one, does it have port 4? Yeah. You see this one? It doesn't have port 4. We can use port 0 and port 1, so it is, because I probably want to use a smaller package one, like this QFN. Does it have port 4? Port 4 doesn't exist. So port 0 and port 1 would be nice. No, not port 1. Port 1 is for this thing. port 0 and port 2. VDIO2. Port 1 needs to be, well, it needs to be, we always need to provide power also when the target is disconnected, so we can use SVDIO. Yeah, port 0 and port 2 seems to be nice. Do we need something from here? We need port 2, we use port 2 for all the ADC on my board. Can I put all the ADC, oh wait, I need a comparator op amp, that's an amplifier, external reference, success approximation, external reference, we don't use an external reference. Oh, that's port 0. Yeah, use port 2 on my design for the ADC. Do I have to? No. I could route everything to port 1, for example, where SVD already is. Or port 15. That's good enough. Trace data, I2C. Why does it specify I2C here? That's weird. Yeah, there's also I2C. It doesn't specify SPI or UARTs. Why does it specify I2C? SIO. This mouse, the wheel on this mouse is dead. We'll have to look later for that. Let's keep it to the thing. So, we could add port 0 and port 4 for our prototype. For the other one, we could, yes, port 0 and port 1 we can't. This is VDD. Port 2 we could. No. VDD2 is P15. P15 we use it. But maybe not these pins. Which one do we use for P15? We use 0167. 0167. Okay, so we can really use port 2 for our device, and this is future proof in case we use this one. Because this doesn't have port 4, but it has port 2. It has port 3 also. Port 3. Yes, we could also even use port. Yeah, it's this port 3. No, we can't. Port 3 we require it. So it's port 0 and port 2. Port 4 could also be used. I will add a note that we could also use port 4. Yeah, let's use port 0, this one, and port 2, this one. And the VDIO, we could add nodes. Yeah, I will add it here. I will add the table here, because I will always forget. Let's put this. Damn it, where is it? Where did it land? Here. Let's put it here. Let's put the table, because it is important for the design. I will put the table here. VDDIO 0, port 0, all the ports, yeah. Port 4, I can copy paste, that's easier. We can always disable. Actually, what we can do is make the text orange. Where is it? Selection, I think. and everything which is orange is not exported. So when we edit the schematic, we see it. When we export the schematic, we don't see it anymore, because this is only important for the design. It's not important for the user. It's important for me. So we can have this colored text. Close. So what we need is port 1, 0. This is here, VDD1. VDD1 needs to be connected to 5 volts also. That's for sure. Now, we also have P15.0 and P15.6. P15.6 and 7, this is already connected. It's VDD0, and P15.0, it's VDD3. So VDD3 needs to be connected to 5 volts. Because we always need to power it to have it powered. Now the two remaining ones we connected to the target voltage. Do I have basic device, power rails? Yeah, I need custom, generic, VCC, but we won't call it VCC. Can I change the name? Yep, I think I can change the name. Yeah, value net. Does it change the name on the schematic? I hope so. Visible, it is visible, yes. V targets. Yes, that's the target voltage. It will be provided by the user, and it corresponds to the target voltage. It's between 1.5, 1.7 and 2.5 and 5.5 volts. What I also have, I do also have a couple of other things I need to add. That's for later. Next. Target voltage. Make it halfway visible. Okay. So we can use port 0, port 4, and port 2. VD2 and port 2. Yeah. What we need is also what I've added. Where is it? Let me show you. That's not the thing. That's the demo. What I've shown here, the analog parts. I do have a voltage comparator, meaning that if the target is disconnected, the analog voltage comparator will immediately issue interrupt request, and the ISR will disconnect all the pins. We need this voltage divider so we can detect that the target voltage is below the threshold voltage. Yeah, voltage threshold. The analog comparator, can it be on, it's analog routing, so it can be any of the pins. That's good. But it needs to be powered. And the ADC, we need an ADC. So these are the pins now I need to connect before I connect the digital pins. Voltage target in, this is to measure the voltage targets, and yes, this is just an analog multiplexer on the analog multiplexer. This goes here. So we need to design the analog part. Can we put everything on these pins? VDD, IO, no, VDD, IO2, 5, 4 and 3 are target voltage. We cannot use them for that. We can use 2 and 3 for the comparators. The comparators, it's analog routing. The comparators should op amp, that's operational amplifier, I don't think. Minus plus, we need to be connected to the operational amplifier. We can route the analog domain. We have plenty of ports free. Port 1 could be used. The port 1 VDIO1 is we can use port 1. I also want to have an external, I don't have any component for that, but I want to have external flash. We also probably will connect it here. Target voltage, let me think. Wait. This needs to be target voltage also. Yeah, this needs to be target voltage. So we need a third port which is connected to this thing. This is important. And yeah, this is target voltage, and we also need a pin. So this could be, this is any ports, but this needs to be target voltage. Domain, that's important. So this is this which I meant was the pull-up resistor, pull-up and pull-down resistor. And since we pull up to target voltage, I need to use target voltage ports. So let's name some pins. I forgot VTRG. It needs to be called in that name, although it doesn't. How do I call it in my schematic? Let's keep this away. Up. Voltage target in. Yeah, and voltage target threshold. V target in. VTRG in. VTRG in. That's connected to voltage targets. And this will be connected to the voltage divider. VTRG threshold THR, how do they call it? THR, yeah. Resistor in use. We can reuse the one which are in use. Since we already have 10 kilo ohm resistor for this pull-up, we will continue using 10 kilo ohm resistor. No, I could just reuse a 10 kilo resistor, although it is not optional anymore. Optional, that's not true. This is mandatory. And we create a 1 to 3 divider. This allows us to have text 1.7 volts and everything which goes below 1.7 volts will be detected as too low voltage, and we will disconnect all the inputs to protect them. And the program doesn't allow you to do anything on the channels as long as the target voltage is not connected. That's one thing done. The other thing was the ADC. It needs to go. We can have the ADC out here. There is. It's on the other screen. Yeah. ADC outs goes to ADC in. Okay. Here. There you see. But ADC pull, CHA out and CHA in can go here. CH, so channel analog out which is the output of the multiplexer, is connected to the VH and N is connected back here, and we add a test point. TP, does it exist? Library test points, yep. This allows us also to measure the voltage. To debug it. This is really just to debug. To be sure that the measurement is correct. Because the analog routing is not perfect. It has some internal resistance, and you need to be able to measure the internal resistance. I do have a calibration procedure which does it, but this will allow me to actually check if the calibration procedure is okay or not. And now we also need the pull-up here. We need to be able to pull it up to the VCC. So we need to use a pin which is connected to either VDIO0 or VDIO2. VDIO0 uses port 4, port 12. Port 12 is on all of them, I think. Is it? Let me check if on the smaller version there is port 12. Port 12, yes it is. So VDDIO0, port 12, 2 and 3, are they here? Port 12, oh, there's 4, we can see even the symbols here. VDD is connected here, VDDIO, which one is it? VDIO1? It's not clear. But we don't have VDIO1, we have VDIO0. Here, SIO, port 12, 2 and port 12, 3. Yeah. What did I say? 12, 2 and 3. So let's use port, yeah. And this will allow us to pull up and down, and this way you can do the resistor on the line. 12, 2. So let's check. 12, 2. 12, 2 is connected to VDIO0. VDIO0 is connected to the target voltage. Yes, works fine. And we decided port 0 and port 2 will be connected to the channels. Do we have everything on the microcontroller? Let me check. No, we don't have the SPI. We don't have the, how is it called? SPI, sorry. The SPI external flash. We don't have also the LED and the push button, and I need both of them. LED. We can keep using the push button. All port 1, yes, we can continue using port 1. And then what is connected on port 15? 15, 2, 3, 4. Okay, it's different things. What is connected? So we have VDD, it's all 15, this is used. VDDIO1 and VDDIO3, VDDIO1. We can use port 5 or port 12. Port 5. Is port 5 available on the smaller one? VDIO1. VDIO1. I think now it's VDI, yeah. Port 1. We already use all of it, almost. Do I have SPI flash? Now do I need to create the parts? SPI, no, spice, flash. 15C something. There's a generic device. That's nice. Net name. Pain in the ass. I will create another device either way, but yeah, we can use this one for now. Because here, so the net name, we need a net name which is called ground 4. How does this work? And VCC connected to 8. So we need something which is called VCC and something which is called ground. I think here we need it to call 1 also. I think I've got bitten by that. Then on the component you need to specify which line is connected. LED, do we sync or do we source? Source. On the development board we source. I think on my board I will think, because thinking is always a bit more efficient. I will pull it. P1 is always BDD1, BDD1 is also so P1. We will all add a limiting resistor, something like 470. How much do we add here? I don't. The LEDs are very bright, very efficient. What do they use here? Oh, almost 1K, and it is bright enough. We can still change it, but if it's red LED, it will be. But we'll use a blue LED. Red LED is for me for power. You can use a green LED. Either green or blue. Green is for me detecting if something is okay, and blue LED is to detect some activity and so on. So yeah, the status, the power, for me power is red, status is green, and everything which is activity related is blue, and we will use it with activity related. So, net name, we will use this one for now, we can still change later on. We know this one works. LED. We will have 5 volts. It goes through the LED, then through the resistor, in use resistor. Again, it goes to the LED wire. I don't know what color, I don't know what resistor, and it is really not important, so I will do it by hand. So something around 1K and something around blue. That's add attributes, value blue, because it's very often indicates LED, but the blue very piercing. And here we will add something like 1K. Add attribute, value 1K. Don't want it to be bright, it's too bright, but we will check. That's done. The switch. Do we have a switch here? No. Push button. The switch allows us to trigger some, for example, to trigger externally trigger a reset, trigger the reset on a channel, or simply to start into bootloader mode so we can flash it, force the flashing. Button, is it called button? Button 6mm, that's mine. switch button here, normally open, it's this one. Push button, okay, switch, let's use this one. But yeah, we have something like single port, double throw, that's not what we have. We have something with 4 pins, yeah, like here, we have something with 4 pins. And there is no double DPDT, no, there's no. And the 6mm buttons are DPDT. Cancel. So this will, we will put a pull-up resistor on here. Up. Let's call it SV like switch. Add attribute SV like switch. Up. This will be connected to ground. When we press, we connect to ground. That makes it easy. And we need a 10K to pull it up. And we can connect to 5 volts. Let's copy it. Even if it's just next to it, let's copy it so we can separate the designs and align them how we want to. 5 volts, and the next, the name, our attribute, switch. We can also use the internal pull-up resistor here, and the internal pull-up resistor is 6K, so it's even less than that. So this could be optional. For now it is not. That's good if it's not always optional. It's a resistor, it doesn't cost anything to put. Now we want to put this device. This will always be selected. We don't need the slave selects for now. We will have, no, we don't have. So we save 1 pin, we don't have to route 1 pin. Write protection is enabled when, let's take a data sheet of a SPI memory. Data doc, data sheet. I see. So I'm sure I have a data sheet. I see flash maybe. EEPROM flash. Okay. Yeah. Very popular data, very popular chip. So write protect, I think it's active low, but you can, yeah, write protect inputs, okay. So yes, quad SPI, we want to use quad SPI, we don't need to be fast. Write protect, yeah, tell me how it is. Write protect, come on, here, chip select, this is active low, this is what the CS does. Serial input, here, write protect. And spits and status. Come on, you don't tell me if it's active high or low. It is active low because of that, but what is the default state? Is it pulled up? Do I have to connect it? This also needs to be high. So this is active low. This is kind of a reset chip actually. Do I have to connect it? Is it pulled up? Is it pulled down? Oh, let's check. need to put it up. I protect. Here. If VPP and hole are attached directly to the power supply or ground during standard SPI operation, the QE bit will never be set to 1. What's QE? Quad enable. So we can tie it high. We don't even have to use pull-up resistor actually. We can tie it high. I forgot. That's a pain. Let's have a look at, no, not this. This is done. Let's keep it open. Here. Problem with this, although, I'll explain. Maximum ratings, no, it doesn't contain any sheet. Yeah. Win bonds. Think of the features. Okay, maybe it's in features. Here. This uses 3.3 volts, not 5 volts. All my I/O at 5 volts, not 3.3 volts. So to do this properly, I would need to have a 3.3 volt power domain for this thing to work. But in real, actually, most of them also operate at 5 volt without issues, as far as I know. I've operated them at 5 volts, but it's above the maximum rating. That's a pain. Where are the maximum ratings defined? Here, absolute maximum rating, 4.6 volts. I've seen it work at 5 volts. I don't know if it works for a long time at 5 volts. So ideally I have a 3.3 volt domain just for this stupid device. Can I put port 1? What is on 12, 6 and 7? I can put port 1 on 3.3 volts. I would have to move these channel things to something which is not which is 5 volts, so something which is connected to port 1, which is connected to VDIO 3, something which is connected here. Yeah, I have enough pins. I will do that. And most of the SVDIO adapter I know are 3.3 volts and not 5 volts. Let's do that. Power rails, 3.3 volts. Close. So let's put port 1 on 3.3 volts. Port 1 is VDIO 1. Up. That means that we need to move these things because they are above. We need to put them to something which is on VDD or VDIO 3. Port 3. Port 3, there are a lot of pins available on port 3, and port 3 is also available here. Yeah. VDIO 0 to 3. 0, 1, yeah, we can put it on 2, 3, but not 4, 5. We need, how many pins do we need? 1. That's always, yeah, let's put it also. We don't, in theory, we don't need, but let's put it 1, 2, 3, 4. We need 4 pins. VDIO 3, it's put 1, 2, and then 12. we can do this way. I will do it this way. Up, undo. So these two will be on port 15, 2 and 3, right? Yes, 2 and 3, that's possible. Up. These are on 5 volts. And now these two on port 12, 0 and 1. Ah, damn it, symbol. It's readable. It's really not ideal. Let's get it a bit higher. And let's reroute the signal. Okay, this thing goes here. So this is 3.3 volt domain. Switches and LED, they can stay here. VDDIO1, VDDIO1, 3.3 volt, that's fine. It's just that I need to put 3.3 volt here. And they can stay here without issues, but they're limited to 0.3 volts. Okay, and now we have 1, 2, 3, 4 pins, and 4 pins is what we need for this. What happens to you? Why are you red? So now we do it correctly, and we have hold is now auto at 3 volt, and so is write protect. So the thing is never write protected. Up. Oh, it looks ugly. Let's do it this way. Up. This is never write protected. This is always write enable. And since hold is high, it's not on the reset. And we just need to provide clock. This is Mosey. No, that's clock. SCK. Then we have master output slave input. We need the chip select. Although, yes, we need the chip select. Sorry. Up. And we need also VCC connected. So we need chip select because this configures when when a thing starts, when a transaction starts. CS. Okay. And this will be master input, slave output. And I think here the SO stands for serial out instead of slave out. Up. And now we can put to any of these pins. It doesn't matter, we'll probably change it to have an easier routing once we do the board layout. Because of the digital routing, we can route it anywhere. Up. Up. Okay. Can we make this a bit more beautiful? Let's have them aligned all on the right. Oh, this one was already aligned on the right. Up. Ah, damn it. One space. Up. Okay, this is done. Well, now we have flash memory. The flash memory will be there to contain some information. You've seen that I'm able to decode the ID code, and I will have a database responds to which chip. And since these are a lot of strings, a lot of vendor names, I will have it in external flash. And this allows me to put a lot of other information if I need to. External flash is very cheap compared to internal flash. And I think this one has only 128 kilobytes of flash. That's enough for my firmware for now. If I continue to extend it, it will be a bit short. This is why I can still put all this, I can try to put all the strings on the external flash and keep space on the internal flash. So everything which will be there. Okay, last part, and then we are finished, is the I/O. So we need plenty of them. We need 4 of them. 4 times 4, 16. And we need a connector. Up. 1. How do I put them? Don't care. 2, 3, 4. This will be protected by not voltage target but 5 volts. So they are always enabled. Now we can start adding the channels. Ah, no, we can't. Not yet. Ah, I know how to do it. I'll do it now. Yeah, I will do it this way. Channel 1, channel 0. Add attributes, net name, channel 0. One, 2, 3, 4, 5. So we will add ESD protection on all the pins. What mostly happens, of where I've seen it, is not actually against ESD, but really against, for example, if you have two different power supplies and they're floating, when you connect the grounds, they will start to stabilize, and there can be a lot of current. For example, if there is a weak isolation in the AC line, or if there's a class Y capacitor against the transformer to suppress noise, then there will be different potentials, and then through the ground pin they might go some huge voltage until it settles down. This will also help that if there's a too high voltage on one of the pins, it will not fry the board, but it will go to ground, and then it will try to stabilize using on one of these IO pins. This happened to me, and I fried a board because of that, because I had a power supply at one potential and my USB hub at another potential, and this was really painful. And if I would have one of these devices, it might not completely get rid of this issue, but it really helps. Cat 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And now all the channels are protected. And so what I did on, how do you see, can you see this? Are they actually here? Yeah, here. What you can see on this device is I have plenty of resistors here. These are inline limiting resistor, so because this microcontroller can put, I think, 40 milliamps per pin, so whenever you have an output, you could put 40 milliamps on the target board. That might fry the board. This is why I have inline limiting resistor. These are 150 ohms. Very often you find 100 ohms to 200 ohms. It really depends on the current which you can sink. On this device, you can actually configure how much current can sink. Let me show you input, outputs, no, channels here. And here I have output, yeah, current, 4 milliamp source. So I can have a lower resistor. A lower resistor is good because whenever you want, if you have high resistor, it takes time for the signal to go high. The lower the resistor, the faster the signal goes high or low. This is why you want still low resistors, but it always depends on the current capabilities of the pins. Here, I think this is 20 or 40 milliamps. I don't remember. We have 4 milliamps sourcing and 8 milliamps sinking. So I can have something which is 10 times smaller. And what it also helps is against ringing. If you have very high-speed protocols, you want to have no ring. And this is particularly important because you have no idea what's on the other side. It could be completely high impedance. You would have high ringing on the pin inputs, which could double the voltage on one of the pins. Very short, very low current, but it can still do it. And for high-pitched signal, it might deform the signal, and it probably will not cause any damage, but it might deform the signal. This is why we will also put resistors, protection resistors, for limiting the currents and for preventing ringing for high-speed signals. And like USB, we will use the same resistors, 22 ohms. So we will have plenty of them. Let's make it more readable from the start here. Resistor 22. Let's put it here. And let's put it here. So the ringing is very important. It's hard to calculate a really good value because I have no idea how long the cable will be connected to the target, because this is not a fixed setup. I have no idea what kind of cable will be used. Is it coaxial? I have no idea of the impedance. But a general value like 22 ohms is perfectly, is probably fine enough. So we decided on port 2 and port 0, I think. Is right? VDD 0 and VDD 2. Yeah, port 2 and port 0. And here we reverse it this way. Okay, that's done. Now we need to connect all the lines and then all the channels. And to have added the resistor next to the pin instead of next to the connector, because this indicates that you should put the resistors. This indicates that you should put the resistors next to the pin, because this is where you will dampen most of the ringing. Okay, now we need to add the ports to our device. Basic, so connectors. Will 22. There's not here 22. That doesn't look nice. No, I think it's in header. Header. Else I will generate. I think at the end I will generate my own 22. Yep. What's the difference? Is one smaller? No. Oh, that There's 3 of them. The pin. This header. So this will be the header which we connect to the targets, and this now becomes important. What I often do is I tie how do I want to do it? I try to tie pin 1 to ground on my devices, on my designs. Yeah, I'll do that. I'll tie pin 1 to ground. That's also what you can see. Now here it's not done. Yeah. Pin 1 ground, pin 2 targets. And here, this is a reset pin. This is to hold the target under reset. And this only worked with open drain system. So we will have okay, so we don't need, so we have voltage targets. This goes here. So we will have the target voltage on the opposite of ground. And not here, because if you switch the connector, you could create a short. Here you can create a short. And we have only 16 channels, we have 16 channels. So this will be channel 0, then we have channel 1. So like the pinout is done, like the pinout left, right, channel 2, channel 3, and go up to 16. 5, 6, 7, 8, 9, 10, 11, 12. I think, let me check. I think in JTAG it's not done the same way. Let me get a JTAG adapter. So, yeah, ARM JTAG. On ARM JTAG, NC is actually connected to the reference. And then 2 is not connected, or 3.3 volts. And then we have all the other pins. Do we want to do it like JTAG? No, I like having pin 1 ground. It's easy to remember, and ground is always the thing you want to connect. What we also want to do is actually be able, we will provide the voltage, because sometimes on some target, for example, this, if we use our device to flash a chip, not only to detect the target board where the chip is already mounted on a target board, but if we just want to flash a chip, a microcontroller, or something like that, we want to be able to provide 5 volt to power it. So we will provide 5 volt, and we provide 3.3 volts. Everything which is below is generally, so let's do it this way actually. So have 5 volt next to ground, because this is often the power supply you want on devices, and then you have voltage regulators. And let's have 3.3 volt against 2 target, so you can, because target device are often at 3.3, microcontrollers are often at 3.3 volts. So we have this, and what we don't have yet is, okay, I did something which I don't want to do. This voltage target 1, it will help us. We will put, this will not be the voltage target immediately. This will not be connected to a voltage target. I'll explain why. So, if we want to provide, we have always to provide, so this requires voltage target to be connected, to be provided by the target. But sometimes you don't want the target to provide the voltage, but you want to set the voltage to the target. And for this, what we will do is we will add a connector which allows you to connect the the most common voltages to the targets. So connector, we will add, so 4. It's an 8.2. Is 8.2 available somewhere? Header. Header. 8.1, 8.2, perfect, 8.2. We could actually have, we have plenty of IOs, we could have transistors which control which of the voltages goes to target. I don't want it because it means that it is possible in the firmware to control what gets to the target power. This could lead to a lot of issues. I want the hardware this to be a hardware setting, because you never know if the modem controller sends some kind of random string and then at one point you have 5 volts on the 1.8 volt target output. That would be a pain. So what we do is we have our target voltage on this side. This will be connected to all target voltages, to all pins on this side, and back. And then the user can select if something wrong happened here. The user can select using a jumper which he wants to connect to the target, to our target. Will it be the target voltage, the real target voltage? Yeah. Can we do that? Yes, we can do this way. Will it be the real target voltage? Or will it be 5 volts? And actually what we could do is actually allow that to target voltage. No, we don't want that. That could be hazardous. We don't want that he will be able to connect our 5 volts to the target voltage. Again, too hazardous. So we only want that he can set the target voltage here. If it's the target voltage of this device, because he can power using 3.3 volt. Yes, he could cheat with 2. Okay, we'll do it this way. We have 1.8, 3.3 volts. So in theory, he can provide target to the board using the 5 volt or the 3.3 volts, and then generally you have a voltage regulator which does 1.8 volt. What could be also useful is to actually provide a real voltage target with 3.3 or with 5 volt, 3.3 volts. For that, you could cheat. You could connect the jumper between 1 and 2, meaning you connect our internal voltage target to the external voltage target, and then you connect another jumper, for example, on here, and this connects the 3.3 volts through the voltage target to actually the real target. And what we also want is 1.8 volts, because I have seen more and more devices which have 1.8 volts and it doesn't exist. So we will copy this one, and since this is an end name, we have to call it 1.8 volts. And we will have 1.8 volts also. So we need 2 things, and I think I have them. Also, where does the 3.3 volt come? We are using 3.3 volts here, we are using it here. For now we have nothing which does 3.3 volts. We'll fix that by using, so we have to quit this, and we have to add 3.3 volts. ls library vreg. What do I have? Yes, okay. I know I have this one in stock and this one in stock. add voltage regulator, Torx. I have to check what kind of variants are available. Variants? Okay, there are no variants, there's only one. Okay, so we added this voltage regulator. This is a really small voltage regulator, but that's good enough. And we want to add another voltage regulator. I think it's this one. Well, I only have this one. I only have it in 3.3 volts. I would like to have it in 1.8 volts, but for now I have this one in 1.8 volts. And I think this one has the several forms. And which one do I have? M5 or MT? I never remember. My stock voltage regulator, low dropout. Yeah, M5. So we've added the voltage regulators. Okay, this voltage regulator has an issue. Pattern. Yep. The YAML was not complete. Now it works. Like library. Lepton. That's not lepton, and let's add the components. We have this one, and we have this. No, it's this one. This is the device, and the value and attribute value. It's yeah. That's the one. That's 1.8 volt output. Okay, and then we have this one, which is 3.3 volt output. So yeah, this one only outputs 200 milliamp. That's not a lot. It's sufficient for most of the thing. This one outputs 300 milliamps, so 1.8 volts. That's good enough. So schematic, come here. Add attributes, value, up, and so we have our voltage regulators. The outs. Oh, is enable high or is enable low on this thing? So here, for example, we could control if we want to output, when we want to output 1.8 volts. We will always output it and not have it software controlled, because the user has to select when he wants to use it. That's good enough. But we have to check if, I have the data sheet somewhere, we have to check if this is enabled high. I think it is enabled high, so we will connect it to high, but we will check. Data sheets, yeah, that's this one. That's the device, enable, it can be left floating. Okay. Enable inputs, logic low, logic high, it's 1.2 volts, but it seems it can be enabled floating. EN, damn it. EN, enable voltage. Enable inputs here. Enable pull down resistor. Oh, there's a pull down resistor. Okay, let's check how this enable pin works. Here. Oh, it is enable high, but it has a pull down resistor. Here, output, enable input, active high. Do not leave floating. For this one, for make have internal pull down, and this pin may be left floating. But it is left floating, it is low. What? Enable input. It is active high. For this one, have internal pull down resistor, and this may be left floating. I don't understand. If it's floating, the pull down resistor will pull it down. It will switch off. I have no idea why they do this. Why they added that. Enable input, active high. High is on. Have an internal pull down, and this may be left floating. There's something completely wrong here. That's enable shutdown. Active high then allows regulator to be disabled. Forcing, maybe there's a sense. Oh, it even discharges the capacitor. A floating pin might cause an intermediate state on the output. To disable the output. Yes, exactly. The mic have an internal. So it can be left floating because. Okay, now I get it. It can be left floating and it won't cause any noise because it is not completely floating. But if we want to enable it, we have to pull it high. Get it. So we will have the inputs. This will be. There's something wrong with this line. Up, and we need a 1 microfarad capacitor. And yeah, we could also add 100. So let's see what the design says. I think 1 microfarad would be enough. We need ground. Up. So this design. This design has only 1 microfarad capacitor. Let's check what they say. In the recommendation. Capacitor, discharge external capacitor. Okay. Input capacitor. Okay, there's no need to put an output capacitor. There's no need to put 2 capacitors. Sometimes you add 100 micro and 1 nano. 100 nano and 1 micro. In this case, it doesn't seem to be required. And actually, we want this capacitor to be next to Vin. And it's really important that it's next to Vin. Again, on one of my very first electronic design, I had no idea what these capacitors are used for. I knew they were required, but I didn't add them next to the voltage regulator, and it started oscillating. The voltage regulator started oscillating simply because the capacitor was too far away. So it is important that you put it really next to the voltage regulator. And same here. And this one is a lot simpler, but this one doesn't have any real pin, and it's a lot cheaper. Maybe I will buy this one in 1.8 volts, so it looks cleaner. I don't know. I have stocks of this one. Why not use it? has enable, and yeah, because we don't need the enable pin, and for maybe other projects we would need the enable pin. I'm undecided yet. I will check. I'll just check the price and the availability. If it's available and if it's not too expensive, I will buy it. And this is done. This is the schematic. It now needs to be like put in the right boxes. Here I need to add some comments, but we've played far too long. And the advantage of the script now, right? Okay, it doesn't do all the things IOVoodoo. It cannot do that. But normally it should have done hardware. No, it didn't. Why didn't it do? I don't know. How does it work? Rake. It's not print. It's schematic print. Let me check. Where's my rake file? There's a lot of things which I don't need anymore here. Schematic as PDF. It's called prints. Schematic and layout. We only want the schematic as PDF. Rake IOVoodoo the schematic.pdf. And using scripts, I have now. Oh, that's version. I have now a PDF, and you see, no, there's no. We don't. The version should be there though. The revision is not there, but the version should be there. And yeah, now we have the PDF of this thing. We need to make it more compact. But that's what. There's a stray capacitor right here. But for now, it is done. And the low. Some things don't print well. Here, there's an issue with the export. And you see, there's the note. The orange note is not there. Maybe is it because it's orange? No, it's also green. I do not know why it doesn't print these things. That's not my problem anymore. So this is the schematic. I think it is complete. The button is, yeah, it is complete. And next time I will do the layout, but it's not for today. For today, I need on pause for now. Just watch the stream and you see when I will do the layout. I still need to clean this a bit up and decide. And change some footprints. Add an LED footprint. Change this footprint. I don't like it. Add some connectors footprint. Although connectors are quite standard. Mostly for these headers, this is just a normal IDC header. These two. I will probably switch this voltage regulator to having something like this. So I have two of them. Here, there's 3.3 volt output missing. There's one missing. So yeah. Needs to clean up, but the idea is here. And it's done. And for that, I will close the stream and we'll see next time for the hardware layouts. But enjoy the rest of the day.